Assalomu alaykum hammaga. Yaxshimisizlar? Sog' salomat.
Assalomu alaykum. Toshkent davlat texnika universitetidan hammaga rahmat.
Так, ну кто у нас? Уже многие сейчас тогда остальным позвоним.
Assalomu alaykum Nurmaki.
Assalomu alaykum hammaga. Khabibullo, yaxshimisizlar?
Rahmat.
Gap emasdan hozir kiramiz. Qo'yanlarga aytib qo'ying.
Bo'ladi.
Дмитрий Галайко, большой привет из Красноярска. Если нас слышишь. Пока не началось. Так, я, наверное, вот так буду. Дмитрий Галайко, большой привет из Красноярска. Если нас слышишь. Вот, это эхо.
Мне кажется, это у вас еще YouTube включен.
Так, попробуем. Пока не началось. Так. А сейчас?
Вроде без эха.
Вот, да, теперь это было именно из-за YouTube. Дима, у тебя микрофон выключен.
Да, вот сейчас только звук настроился. Сейчас все слышу.
Так,
Дима,
всем добрый день.
Дима Галайко, приветствуем.
Привет
Здравствуйте всем.
Рад вас видеть.
Так у нас расширенное собрание получается, да? У нас не только из...
Да. Так, ладно, я пока отключусь.
Кто-то еще есть из
Чтобы
наших?
не забивать канал.
Добрый день еще раз всем. Дмитрий, здравствуйте. Как вы?
Здравствуйте.
На здоровье.
Всем.
Надеюсь, у вас все хорошо там?
Да, сидим по домам, но в целом все хорошо.
Сидим по домам. Ну, это мы тоже проходили уже. Здорово. Сейчас, так.
Здравствуйте, ассаламу алейкум. Абдуманов Аке. Дмитрий, здравствуйте.
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 Ассаламу алейкум.
Алейкум ассалам. Khabibullo Nosirov charchamayapsizmi? Yaxshi yetib keldinglar?
Keldik, rahmat.
Всем большой привет из солнечного 5-го этажа блока С TUIT.
I would like also to welcome Veronique and Viara from Sorbonne University because there are here people who don't speak Russian.
Hello.
So we are here. I don't know if there are more people from partner universities, but just to point out that not everybody here speaks Russian.
Ну, у нас, я вон Андрея вижу, этого вижу.
There is no sound anymore.
Дмитрий Островерхов, большой привет из заснеженной холодной Сибири. У нас на празднике минус 41-42 было. Как у вас?
Пока терпимо.
Приветствую. У нас, ну сколько, днем около нуля было, ну а ночью, скажем так, минус 5, минус 10.
Хорошо.
Не как у вас.
Да, чуть похолоднее.
Но с учетом поправочного коэффициента, думаю, столько же.
Хорошо.
Очень приятно. Хороших всех лекций. Удачи всем.
Okay.
Dmitry, can you hear me?
Yes, I can hear. I can hear you. Well, I see that Dirk is also here. So hello, Dirk.
Yeah.
Can you hear us?
Yes, I can.
Oh, we can see you.
Hello, everybody from Tashkent.
Hello.
How are you?
Good.
Good. It's very, very good.
And Khabibullo, we are waiting for your reactor. Yes.
Вот, Дмитрий тоже здесь. Дмитрий, приветствую.
Hello, Dmitry.
Hello, Khabibullo. Can we begin? Maybe.
I'm just waiting for our vice rector. Sorry for our rector told us very, very sorry because we have some government events. So he just flew to the Karakal, Pakistan, to our next region for the meetings. This because of our president's meeting. That's why Kamal Tashev is here. And
hello.
Thank you, everybody. I think.
Morning, everyone.
Yes.
Hello, Mr. Dmitry.
Assalamu alaikum.
Assalamu alaikum.
Okay, if everybody is here and we are ready to start, let me just. Thank you, everyone, for joining us, being here, and we are very happy to see you healthy in this very difficult time. And thank you very much for being with us, our Vice President of European Affairs, Veronique Perdero. And let me give a floor to our Vice Rector of Kamal Tashev to speak about our project. If you're ready, Kamal, again, please.
Yeah.
The floor is yours.
Thank you. Good morning, everyone. Dear Honorable Vice President of European Affairs and dear colleagues and participants. On behalf of Tashkent University of Information Technologies, named after Muhammad Al-Khwarizmi, we are glad to see you at the opening ceremony of the online winter school on innovation technologies in space systems and communication engineering within the Erasmus Plus Space-Com project. Today, the world is turning to the technologies to make societies viable and dynamic, to accelerate competitiveness in the conditions of the increasing globalization and achieving sustainable development. In this point, the prosperity of the space technologies and their applications play a crucial role for the enabling innovation in societies from the different perspectives. The Space-Com project is very important for us, as well as for Uzbekistan's role in training leading personnel in the field of space technology. In this project is a great opportunity for Uzbekistan, as for the first time Uzbekistan is participating as a grand holder. This places a great responsibility on the Uzbek group of partners. The online winter school, which begins today, will undoubtedly be one of the great accomplishments of this project. Within the framework of online winter school, we all are here to share our important knowledge and discuss them from the different viewpoints. I hope the online winter school becomes a stage for all of us to exchange valuable insights, results of experiments and research, to contribute to the common well-being of the space technology. Using this chance, I would like to express my gratitude to the Vice President of European Affairs, Mrs. Veronique Perderot, who agreed to deliver her speech at the opening ceremony. And the European partners, especially the Technical University of Berlin company, for the participation in the organization of this ceremony. And the professors who agreed to participate with their lectures, and I wish you the best of luck in hosting this conference. Thank you very much for your attention. Thank you.
Thank you very much, Muhammad. And let me give a floor to the Vice President of European Affairs, Veronique Perderot. Please, the floor is yours.
Yeah, good morning, everyone. So I'm Veronique Perderot. I'm a professor in robotics, and I'm presently Vice President of Sorbonne University in charge of European affairs. So as part of my portfolio, I'm very much concerned with the engagement of our university in the European programs. And in fact, we are very successful because we are the first university in France in terms of participation and funds collected in European programs. But still, starting a new project is not business as usual. I'm very happy to be here today. I'd like to warmly thank the coordinator for having invited our university to be part of this program, and also to thank our colleagues from Sorbonne universities for their engagement in such a program. So thank you very much. So as I said, I'm very happy to welcome you today, but very sorry that this is not in Paris that I'm meeting you, but just virtually. I suppose you would have had a good time in Paris because this is a pleasant city. All I can do is to show you the view I have from my office. So the weather is not very nice, but still, I suppose you're going to see, I don't know whether you're able to see the Eiffel Tower and also Notre Dame over there. So I have a wonderful view from my office, and I'm happy to share it with you today. But I hope there will be another opportunity to meet here in our university. This is a big university in terms of education, research, and innovation. We are very well located, as you can see, in the center of Paris and very well ranked. This kind of program is very important, in my opinion, for our university. Of course, the objective is to share our experience and best practices with you, Uzbek partners, and I hope that it will be very fruitful for you. But I would like to tell the European partners that they will also take some experience and best practices from you. This is a true exchange. This is not just a one-way collaboration. And that's what I discovered recently. I will tell you later. So today you're starting this masterclass. I hope everything will run smoothly, and that I hope you will be happy at the end of this masterclass with the knowledge you acquired. And I'm sure it will open some other opportunities, not only within the project, but also in the near future within the Erasmus program, because it is starting now, the new program, the new Erasmus Plus program. So you Uzbek partners will be able to participate in some other European projects. And I'm very happy with this perspective. In fact, I'm sorry, have the problem with my headphones. I like to say a few words on a personal note. I said that I learned recently the benefit that we could get from such a project when we are supposed to disseminate our experience, because I was also part of a capacity building project with the Uzbek partners. We were working on the modernization of medical studies in rehabilitation. And for this reason, I went 3 times to Uzbekistan. I visited, from the partners, we were having Tashkent medical and technical universities. We also had the Kashi branch, and I traveled to Nukus from the Karakalpakstan Republic. And on personal basis, I visited Samarkand and Buhaha. So I know quite well your country. I liked it very much. And I also enjoyed very much the relationships that we were able to build together. You're very friendly, very friendly people. You have joy, and that's what I appreciated a lot. And I recently said to my husband, when we will be able to travel again, I like to spend some holidays in Uzbekistan, because I felt emotionally, I would say, that I could have good time again in your country. So I'm very happy to welcome you virtually today. And I hope that next time we will be able to have more fluent discussion. What we are missing with this virtual world is the time we can spend during coffee breaks and have some discussions, informal discussions. And I hope that I will have this opportunity next time. So I will not stay very long with you. I have another meeting, but I wish you a very fruitful meeting. I wish you the best for the period you're spending together. And again, I'd like to thank you for inviting me for this welcome note.
Thank you very much. Thank you. We are very appreciated that you know our country. And you are welcome. And we hope also this pandemic will be ended soon and we could meet. And we are welcoming you in Uzbekistan. Thank you very much. And if you agree, I am giving...
I just say goodbye.
Thank you.
Enjoy.
Thank you very much. Thank you for your time. Thank you. Let me give a floor to our partner from Belgium, Mr. Dirk van Marodi, with his topic on FPGA for space applications. Dirk, are you ready?
I'm ready.
Yeah.
Give me just 1 minute because I need to put on my repeater. I'm at my home office, so I also have a nice view. If I look outside, I can see the park or the buildings from the park where the campus of AP is situated. So I am still a little bit connected visually with the campus. But as in many places, we are working a lot from home at the moment. So, and I'm also connected to Uzbekistan through the world map. So like this. Let me first put on my repeater because it happens sometimes that the Wi-Fi connection is bad. So give me just 1 minute and I'll be back.
Okay.
Less than 1 minute.
Go fast.
So, yes, I would like to share my screen with you. Let me first put on my presentation. And then we're off. I'm going to put you guys on the other screen.
No, you can. It is allowed.
Okay. Do you see my presentation?
Not now.
Not yet.
No, not yet. Okay. Okay. Now you see it.
Yes. Yep.
Okay. Yeah. We most of the time we work with teams a lot at our university. I'm not so well experienced with Zoom, but the idea is always the same. So that's a nice thing. So I would like to. I also would like to express my gratitude to having me here. So and giving me the opportunity to talk about something that I like to talk about FPGAs and their applications in space. So I hope I can teach you a lot, but I also want to take the opportunity to talk a little bit about our university for the first couple of slides, and then we will get down to the more practical business. Okay, so this is me, and this is me on my first day at AP. So I only moved recently. Now I'm in my third year that I work for the AP University of Applied Science and Arts, and I'm the international project coordinator there of the IT department. I moved there from Thomas More, another University of Applied Science and Arts in Belgium. So some of you maybe still know me from that because it's not my first project that I do with Uzbekistan. So at the moment, I'm also a project coordinator. So we can for sure help each other in more practical matters, for instance, in administration of such a project. I'm running the ACTIA project with African partners in East Africa. And of course, I'm also a member of the Spacecom project. This is me and my boss when we were in where was it? In
Samarkand.
Samarkand, yes, that's the one. Yeah. I was thinking Samara, but it's Samarkand. Yes, it's true. So we also have a Key Action 107 project with a university in Tel Aviv and with a university in Zaporozhye in Ukraine. And as I already mentioned, we are also quite active in Africa with the ACTIA project, which is in Ethiopia, Tanzania, and Uganda. But I also am the president of a non-profit organization where we help to build a primary school for deprived children in Uganda next to the Congolese border. We also have a healthcare center, a little hospital, and a vocational training center for young people. So I have two main focuses. So I did a lot of projects in Eastern Europe, as you can see, and these are all well-known countries. A lot of these projects were done with the our partners from TU Berlin. So some of these projects will be quite well known. And then we have our focus in Africa. The first thing that we did there was to build a radio station for the university to spread the knowledge of the university through spoken word, because you have a lot of analphabetic people in Africa, in the community around Fort Portal. And that's why we use a radio station to share some of the knowledge of the Mountains of the Moon. I think I really like the name of the university. It's the Mountains of the Moon University. So to share some of the knowledge. And now we are doing this big European project, Applied Curricula in Technology for East Africa, which is all about implementing curricula in technology, mainly in CAD/CAM systems, automation, electrical engineering, and renewable energy in these countries. But a very important part is the applied side of this. So we do this very applied. It needs to be as practical meanings. It has to be very well connected to local industry and so on. So at AP University, I teach digital fundamentals. I also teach at the moment, because it changes quite often. But now at the moment, I'm teaching digital fundamentals, FPGA programming, Arduino programming. So that's more about microcontrollers. And then I also teach software-defined radio. But I also had a past in satellite systems, but also in audio video production, PCB design, and things like that. So let me first introduce our university a little bit. So maybe you know where Belgium is, but maybe you don't. It's just a small country between some of our big brothers. So we have our neighboring countries are France, Germany, the United Kingdom, and Holland or the Netherlands. So Belgium is a country in between, and the upper part speaks Flemish. The southern part speaks French, and so I'm from the northern part, from Antwerp. So if you would go outside in Flanders, you would see something like this, if you can find these kind of landscapes, because Flanders is quite a densely populated area. So we have a lot of people there. So we also have a lot of, and it's been being densely populated for a long time now. So we have a lot of these medieval cities in Antwerp. So the top part here, this is Brussels. This is very well known for the tourists. It's Bruges. Then you have Mechelen, which is an old and important, historically seen important city. And at the moment, I'm working at Antwerp, and I'm also living at Antwerp, which is regarded by people from Antwerp as being the nicest city of Flanders. Opinions can vary in Flanders, but we think so in any case. We're quite proud of our city. And we are also proud of our food. So Belgium is known for its waffles. This is some kind of stew, some kind of goulash that we like a lot. Everybody eats this in Belgium at least once a couple of weeks. And then you have the Belgian chocolates. And obviously, we're also very fond of our Belgian beers. Maybe you don't know this, but Belgium is very renowned for its special beers. And also here, there's some discussions with people from Germany and people from Czechia. They all say that they have the land of the beers, but in any case, our beer culture is voted cultural heritage by the UN. So now everybody can say what they want, but if you're backed by the UN as being the land of the beers, then probably this should be, then this is the case. Now to go a little bit more into AP. So we are a practice-oriented University of Applied Science. We have a research center. We are a research center, but also very much aimed at working together with the local labor market. And we offer level 5, 6, and 7 higher education. So at the moment, we have about 15,500 students, 11,000 in level 6 and 7, but recently we also are providing level 5 training, which is even more oriented at the labor market, but very specific. So very specific job oriented, while the others are more generally, so you have a more broader theoretical background. And our campuses are spread all over the city of Antwerp. So if you have the chance to visit Antwerp, it's not such a big city. It's about 400,000 inhabitants. So you can easily go from the one side to the other side. You can do this walking, but we prefer to take our bicycle. When I got married with my wife, we invited people, and we could do this on one evening with our bicycle. So it's not that in area. It's not that big. So obviously, we are located in Antwerp, so we have a regional but also a very international focus, because Antwerp obviously is a very international city due to the World Harbor that we have. We focus on personal growth, both of students and staff. We need a good combination of theory and practice. We like to work a lot with all other departments, so multidisciplinarity is quite important. We are a very multicultural higher educational institute, because we have a lot of people with foreign backgrounds, and we do believe that through training and education, life conditions of everybody will improve. And we also are a center of expertise for the Antwerp region. So also to have strong links with the labor market and with innovation, that's quite important. Now, as a consolidated university, because we were two separate institutions a couple of years ago, but now we're consolidated in one big entity, which means that we also offer a very broad range of specialties in higher education, ranging from science and technology over dance, music, social care, and so we have a very broad scope of topics. So, which also means that everybody can find something to relate to. If you want to work together with AP, you can have a lot of different subjects to pick from. So AP is also very internationally oriented, which means that we focus a lot on international competences of the students, and we embed it as much as possible in the curriculum. It's not that we just provide the conditions for our students to go study abroad. No, they really work together in international projects with other students from all over the world for their multidisciplinary projects, so that it is really embedded in the curriculum, and it's really something that is a part of their studies. So obviously we have student exchange, but also we have short mobility initiatives, which will be in the next Erasmus call. We already learned that short mobilities and blended mobility will be more and more important in the new Erasmus. Obviously, due to the pandemic, everybody became digitized overnight. So that's also the reason why people would focus less on long term and more less on traveling and more on international digital cooperation. So we also offer English modules, obviously English programs, and we also focus a lot on internationalization at home. So not only going abroad, but also that internationalization is a part of the curriculum. So this is the skyline. I don't have this view of the skyline of Antwerp, but this is more or less the skyline. Antwerp is quite an important economic center. I just looked for the numbers, and it is 8% of the Flemish gross GDPR, gross domestic product, GDP. So the 8% of everything that's earned in Flanders is earned in the harbor area. And there are 140,000 people working in this area. So, and this is actually at our doorstep. If I look at my campus and I look outside, I look at the beginning of the harbor. So the first ships I can see just from our campus. So it's clear that we work together a lot with the harbor area and the industry and the companies there. And a lot of our research is focused on developing solutions for the harbor. So we have internships for students, obviously. There's a lot of future job opportunities, and we develop long-term partnerships with the harbor. And it is also for a very long period now, has been a cultural center. So this is also why we have a lot of focus at AP on arts, on fashion, also on diamonds, diamond cutting, and things like that. So having or being located in Antwerp sure provides a lot of opportunities. So these are faculty, the Faculty of Science and Technology. At Ellerman, it's located in a big park, so that's quite nice for our students. And the faculty offers level 6 education, level 5 education, but probably the most important or the most interesting part is on the level 6 education. So we have a lot on science and technology, ranging from chemistry over electronics, ICT, energy management, graphic design, safety, and things like that. So I'm part of the electronics ICT department. We merged together with the applied computer science department. So now we are a big IT department. So now we have in our first year, maybe these numbers are not that impressive for Uzbek universities, but we have about 270 IT students starting in the first year. We offer our IT in 4 different flavors. So IT more business oriented, IT and software, which is on software development, then IT on cybersecurity and cloud services, and then IT and the Internet of Things, so more on microcontroller and microcontroller-based systems. So if you would like, you can always look to the links, because maybe this could be interesting for. This is also the reason why we divided this, because we know that that these focus points are quite international, and so so here you have some keywords of the things that we are doing in the different different flavors of our IT department. And so I mainly work at the Internet of Things part, so more on embedded programming, smart applications, IoT systems, and so on, robotic systems. So we also offer international opportunities for students and for staff exchange. That's also the reason why we have these Key Action 107 projects, which are mainly focused on student and staff exchange. Now, for students, we have a nice opportunity, which is called a European Project Semester, which is actually a multidisciplinary international project that we offer the students. So it's international, it's interdisciplinary, it's project work, and it's in cooperation with AP's work field or labor market and the researchers at AP. So it is a full semester module that we offer for incoming Erasmus students, but also for AP students. and it's a mixture of project work and courses, because if you come to Belgium, it would be nice that you learn a little bit of Dutch. So this is put in the supportive courses, and for the rest you work in an international project team. So it's always during the spring semester. So if you want to, because we had some applications of Uzbek students, they wanted to come and study in Belgium, which they are very welcome, obviously. It would be even better if we if this could be embedded in a project, because then they get a grant. You can always, everybody is welcome to come to study in Belgium, and we can sign a memorandum of understanding for exchange. But obviously, you need to know that studying in Belgium and living in finding an apartment and so on, or a student room, that all has their costs, obviously. Okay, so the project will always be a real life project for 4 to 7 students with different nationalities. And it's also important that it's interdisciplinary, so it's not only about technology. And obviously you get coached, and we work together with companies. And then you get courses, so the background of Antwerp, project management, and languages. So these are the 10 ECTS in courses. This is an example of a student team. So we have a Spanish student, Belgian, German, another Belgian, and Turkish girl. So they worked on this topic. It was an app for the elderly. So so they could make an avatar about themselves and get themselves. So it's something to use in the retirement homes and to be interactive with the outside world. That was more or less the idea. So if you want to know more, if you want to start cooperations, send students or something like that, you can always contact one of these people. So the first two are our heads of our departments, both from the electronics departments and the applied informatics department. And then we have 3 international coordinators, me being responsible for the international projects. Okay, so this was the introduction to the AP, University of Applied Science. By all means, you are very welcome. Hopefully, after when the vaccination has gone through all over the world, you get the chance to do some, or to come to Belgium, to come to Antwerp. Hopefully, we can do some face-to-face trainings and very practical trainings that that we can get you up to speed with the courses that we are developing in the SpaceCom project. Okay, let me start with the real content from today about the FPGAs for space applications. I would like first to an introduction on digital systems design on FPGAs. I would also like to give an FPGA market overview to prove that the FPGA market is only increasing in importance, and also to be a little bit of an advocate of this component. It's not the most desired or most popular component due to the fact that it's often a little bit difficult to work with, but I will show you how easy you can get fast and easy results with the FPGA. So I will show you how the FPGA works. I gave a comparable lecture to people from China. They were using an FPGA a lot, and after the presentation, they said, now I finally know how it works from the inside. I think this is a good thing to know. Then about VHDL, one of the 2 major hardware description language used to interface with an FPGA or to implement hardware in an FPGA. I will talk some about digital components, about system on chips, then FPGA in space and the special things that we need to take into account when using microelectronics in space. And then if there is still some time, I would like to talk a little bit about digital signal processing on FPGAs, because this is the thing that are mostly used, FPGAs are mostly used for digital signal processing applications in a very wide or broad sense. And so this is why they are so strong and why they are used so much. Okay, teaching to a diverse audience is always a little bit tricky, because you don't know what people know and what they don't know yet. For people that already know a lot about digital systems design, maybe it's a nice thing to really see what they or to get reassured what they know, or maybe to have another viewpoint on this topic. And people that don't know this, then I hope you learn something new. If you have questions, by all means, you can always ask them. Although I don't see the chat, but I guess some of the moderators will stop me if there are some urgent questions, then they can always interrupt me. Okay, about digital systems design. So digital systems design is actually the process of designing or developing systems that represent information using the binary system. So this means we want to make something that does something useful for us. And one of the most important or well-known things that a digital system has to do for us is making calculations in all different forms. Then we have to decide how to represent our numbers and how to add them, how to multiply them, and things like that. So this is some of the things that we want to do with a digital system. So microcontrollers, microprocessors, memory chips, FPGAs, they are all digital components. And then systems like the ones we are looking at, our PC or our smartphone, they are all digital systems. And here you have some basic parts and some logic gates, which are built from different parts. This is a chip, for instance, and this is also such a logic gate. So if we want to develop a digital system, then we want to have a certain behavior. We want, for instance, something that we can call our friends with, or we want something that does our calculations. Right? So we want some behavior. If you want to have some behavior, we need some kind of structure. We need to have the components that can do this behavior, that can help us doing this behavior. Think about a microprocessor. We want something that can add things together and can communicate, for instance. Right? So add things together is done in the ALU, and that it can communicate results outside or to memory and so on. And so this means that you have complex systems. The more you go inside, the more you go to the basics on how these systems are built. Because if you want to have some certain structure, then you need some kind of geometry on how this is laid out, how this chip is laid out. This is the geometry that we need. And so here you have a more simple, just transistors, and the more you go outside, the more elaborate the things become. So if we want to have an overview on how this design starts, it all starts with white sand, silicon. So Silicon Valley is obviously, it's called Silicon Valley because of the white sand, which is needed to build chips. So if you have a semiconductor material, this is built of white sand. Luckily, this is a lot. You can find this a lot all over the world. The special things are the things that you need to add to this silicon to make it make them semiconductors. But in any case, if you have a proper geometry, then you can build your own chips out of glass. Is actually how it's built. So you can build one transistor, With transistors, you can build a logical gate, which actually has a certain behavior. If you, for instance, this AND gate, if both of those inputs are a 1, then you get a 1 on the outside, then you get 3.3 volts on the outside. And then if you have one gate, then you can combine these gates and make systems like this one. This is an adder, a carry look ahead adder, or you can make a flip-flop out of this. And then you can build bigger and bigger systems, like, for instance, a CPU which consists of an arithmetic and logical unit. And then if you add inputs and outputs, then you have a complete system where then you are building actually your smartphone, or a piece of your smartphone. So this is how it's all connected. And this is another way to show this. So you have the systems, then you have different behavior that you would like. This is a structure that you would like. This is the register transfer level. And where you see the big the brackets or the dotted lines, then this is where you can use hardware description language to model this behavior. Now, on the circuit level, you need transistors, and transistors again are built from circuits or different materials put together in a certain geometry. If you look at this slide, you see this is an overview on how digital systems are designed, but you cannot cope with all the detailed information. If you want to have a certain behavior, you cannot cope with how will this at the end be laid out, how these different materials on a nanometer scale should be connected to each other to have this behavior. And so that's something you cannot keep in mind as a designer, keep everything in mind, because then you will lose yourself in details. So this is why digital systems design always works with abstraction levels. You need to stay in a certain abstraction level so that you can leave out all other information that you don't need at that moment. So you just are working on the behavior. You check if the behavior is working or not, and then you can translate this to the RTL level, where you get more information. Then you can transfer to the logic level, where you get more information, and then you can transfer to the layout level, where you get all the information. Because at this level, you know everything. You know the behavior, but also how it is built together, this digital system, what the length of the different parts is, and so you also know the electrical behavior of the system. But you cannot bother knowing the electrical behavior of the system, timing behavior of the system at this level, because otherwise you will lose yourself in details. That's why we have these different abstraction levels. We leave out. We don't bother about is this something that is possible to build. So we will see this later. And obviously, to go from this level to this level, you will always have some tools to help you and guide you. So that's something that we will see during this presentation. We will see how fast with the tools we can build something working. Okay, so now go to the FPGA part. So a field programmable gate array is a device where we can create our own digital hardware in. So digital hardware can be something like this. So just a couple of gates, an AND gate, an OR gate, and a NOT gate. Or a digital system can be something like this, a complete microcontroller system. Now, both of them can be put in an FPGA. An FPGA is a generic digital hardware, so you can put just one gate in it, or you can build a complete system on chip on an FPGA. So this is why it's such a strong component. And you build new hardware, and hardware always has the advantage that it's faster than software. but you lose a little bit on efficiency because it's so generic with the FPGA. So it is used in a variety of markets, like automotive, industrial. Excuse me. Military, consumer electronics, and others. And it's becoming increasingly important because, as I already mentioned, it is hardware. So we need fast communication everywhere, and the big bandwidth capacity of an FPGA. This is actually where it is. It has its main usage because it can process a lot of data in real time. So that is why it is such an important component because of the high-speed internet search and the increased trend for having internet in rural or remote areas. So when do you use an FPGA? So you can use an FPGA or you can use a microcontroller. So the question is, when do you use an FPGA? When do you use a microcontroller? So you use an FPGA when a microcontroller is not sufficient. And when is that? When you have high-speed data, high-speed processing, digital signal processing, when you need hardware acceleration and efficiency for power usage, and when you have limited numbers, when you cannot build your own ASIC. An ASIC is a chip, a specific chip that does a specific job. Now, building an ASIC costs money, so you need to be able to sell sufficient amounts before you should start building your own chip. I put the picture there is an example of where FPGAs can be used. And this is, for instance, for full HD mixing of video sources. That's where an FPGA, for instance, these are products from Blackmagic Design, and they use a lot the FPGAs for their products. I had somebody from what was the company called again? ST Ericsson, and they are developing chips. They develop, for instance, a chip that does all the RF communication in a cell phone. And they told me developing that specific chip costs 300 million euros. And they sell the chip for 1.5 euros. So this means that they need to sell a lot of chips. This is a very difficult market because you need to be able to sell the chips quite in big numbers. So this is also the reason why an FPGA can be very helpful. So you can use an FPGA to build your ASIC because you can actually, what your chip will look like, you can put that already in an FPGA. You can build your chip, you can write your VHDL code, and then transfer it, translate it to FPGA technology, which means that you already have your chip before it is on the market. Before you have your chip coming from the company, you can already sell the design. So this is why these guys, they brought us the chip in 3 big FPGA boards. So you had a cell phone spread out all over the table. And they can already sell how the chip will work, and they can even start developing their software for a chip that is not yet produced. So this is why the FPGA is also extensively used, and also for a test environment, because your PC probably only has a USB, same as mine has. But you need inside your chip, inside your FPGA, you will need more standards, more ways for testing your design. So this is also why FPGAs are used, because they can do anything. Now, if you look at this chip, this is the part which is developed by designed by the tools. So this is the digital part, and then if you have the more structured part, these are probably an analog front end or some memory and so on. But probably our colleagues from Sorbonne University, they will tell you more about the layout of chips. So the big advantage of an FPGA is that they can do anything because it's reconfigurable hardware. They are super fast compared to microcontrollers. They can be reprogrammed, so they're field programmable once they're on a PCB board. Let me find you, because I want to show you these things. Yeah, as being an advocate of FPGAs, I always have some FPGA lying around. So this is once you have put your FPGA here, this is the one on a PCB, and you have sufficient hardware around, then you can build and rebuild things on this FPGA. They are massively parallel, so which means that you can build hardware which exists next to each other. So that's why they are this fast, and they have a very high input-output count. And so we're talking about 250 I/O gates, which is a lot compared to microcontroller. Now FPGAs are quite expensive because it's a complicated chip to produce. They're quite expensive compared to microcontrollers. Microcontrollers, they are very cheap. This FPGA costs $10. I think a microcontroller you can buy for $1.50, but this costs $10. And this is a low-range FPGA. They consume, compared to an ASIC, compared to a microcontroller, they consume more power. Another downside is that they are volatile. If you lose the power on FPGA, you lose the configuration. So this is the reason why often you can find another chip as a neighbor. This is the one. Another chip which contains the configuration of this FPGA. But this takes some time for booting. It has a lot of pins, so it's difficult to put on a PCB because you have this ball grid area. You need very specialized equipment to put this one on your piece electroplate, your PCB. So, and obviously it's rather complicated. So you have a lot of things that can go wrong. Your tools are quite complicated and complex. It's also difficult to compare different FPGAs because different vendors use different benchmarkings for their quality of their FPGA. And also HDL is not that easy or intuitive to use, especially because it looks a little bit like a programming language, but it is not, because you're developing your hardware. That's also a reason why it's often a little bit difficult to use. But it is used a lot. As I already told you, because of the high-speed internet, high-speed applications that we need everywhere. But this fintech, I was talking to the guys from Xilinx a year ago, and fintech is something new for them. Financial technology, you know that a lot of the buying and selling of stock, so the rich guys from Wall Street, they do a lot of this selling and buying from stock. And a lot of these things are done automatically. They are done with artificial intelligence. So the decision of buying or selling is put into the care of computer systems. And having the edge, having the edge on speed gives you the edge on what to buy or to sell. So this will get you more money. It's as simple as that. Some microseconds of doing your calculation faster than your competitors will gain you millions in fintech. So this is why the stick-to-trade systems, for instance, this is why they want computing power near the trading floor, and the trading floor is limited in space and in energy. So that's why they use FPGAs, because they don't use as much space and power as your laptop, because or the servers. So you can have specialized systems very near the stockbrokers. So that's why they are used a lot. Now, this is our field of interest, obviously, where we use FPGAs or microcontroller systems in space applications. So they are used a lot in space applications. Here you have an example, for instance, the Sentinel-2, which is a big communication satellite. And it uses about 250 integrated circuits, and more than half of them are FPGAs, both in the payload as in the flight part of the satellite. So these are the numbers from people from ESA. So if you see in some missions the amount of ASICs and FPGAs that are used. So ASICs, this means that ESA made their own chip for this mission. And FPGA means that they are using a generic but special FPGA for this space mission. Here you can see why they are using FPGA. So we have the Leon, which is a typical processor which is used because it's a radiation hardened and very stable processor, which is often used in satellites. For instance, in the Proba V, the satellite developed here in Flanders, it is used. And you see only the processor, and then you see the Leon plus Brave. And Brave is an FPGA from ESA. And then you can see the hardware acceleration that you can achieve. So they had a typical application, is a star tracker. So you have a picture of the night sky with the different stars in it. And this can be used to calculate and localize where to find where the satellite is localized in its orbit. So if you do this only with a Leon, you can see it needs 4 hours of mapping and 35 seconds of localization. If you use the Leon plus an FPGA for co-processing for the DSP part, then you can do this in 17 seconds. So you can see the gain made by using actual hardware acceleration of with an FPGA. So why are FPGAs so attractive for aerospace missions? It is quite important for their reconfigurability, because maintenance is hard in space. That's why I use this picture. It's quite hard to do some maintenance or to do some new applications. So if you need some astronaut to walk outside, then it's already quite difficult. So the nice thing about the FPGA is when you put them on a PCB and you make stable and good connections to the outside world, then you can build anything. So you can have late bugs in your system. You can always fix them in a later stage, which prevents you of having to queue again. If you want to have a mission in the International Space Station, it takes you some time to get into a mission to the International Space Station. And if you have bugs that cannot be resolved, then you have to queue again. Then you have to be last in queue again. So this is why it is the reconfigurability of an FPGA comes in very handy, because it reduces costs and development time. If you have something that's malfunctioned in mission, you can always reprogram your FPGA and solve the issue. And you can also change the function. For instance, you have a mission that in the first 2 months has to measure a certain something with the sensors of your satellite, and later on it has to do some communication or something. And so you can always change the functions later on during flight. Or you can also fix problems when you know the flight conditions better. And you can have the same hardware performing different functions in different stages of the mission. This is the reason why ESA ordered the development of their own FPGA, because they see the benefits for having an FPGA, radiation-hardened FPGA of their own. So Brave is the name of this FPGA, and it's a big reprogrammable array for versatile environments. Versatile, you can translate versatile to challenging environments. So they want to have to provide space industry with a decent FPGA, radiation hardened, and especially a European FPGA, because they think it's quite important to have the knowledge about the systems in Europe, because they don't want to depend only from foreign technology, and in this case from American technology. So to have an FPGA capacity so that you can use them in different missions. Again, this is from the reason why they built Brave. So the reprogrammability is quite important, so that you can have design changes or modifications. FPGAs are cheaper. The development costs a lot, but because you can share the development costs over a lot of missions, then the FPGA becomes cheaper, which means that you can also involve companies that they don't have the capacity or the money to build advanced ASICs. So they can use this Brave and also apply for space missions. And so this too, so the ESA don't want to have dependency on the USA FPGA restrictions, because it's not always clear where an FPGA can be used. I think that is an FPGA, because it's such a versatile and strong component, you cannot ship this anywhere. So that's by the ESA, they don't want this. And obviously, to keep the knowledge of building FPGAs, keep it in Europe, so that they have their own capacity locally. That's quite important. So here you see the developed chip. On the left upper side, you see the chip still in a wafer form, and after cutting, then you see the bare chip here, and then it's put in a package to put it on a PCB. And here you have a test model of this test board of this FPGA, this Brave FPGA. So an FPGA especially focused on space engineering. Now another field of applications for FPGAs, that's something that I do with my colleague, and he will also do one of the topics later on in these sessions. And it's about software-defined radio, which is becoming more and more the standard for radio communication. So you always have hard or fixed elements for the RF part. So the antenna, front-end RF hardware, an analog digital converter, digital to analog converter. But most of the functionality is then put in some kind of programmable medium like an FPGA. And if you use a processor, then you like the input-output bandwidth that can be offered by an FPGA. That's why FPGAs are used a lot for software-defined radio. And so if you look at the modern solutions for these radio systems, then you can always look for the FPGA. So here is this Altera chip here too. It's also from Altera here too. So Altera is doing very good in the software-defined radio segment. Now, if you see the advantages of an FPGA, then you can also see how this market share, how important the market share of FPGAs has become. And depending on the source, you have a annual growth rate of between 8 and 14% forecasted. Now, if you see this, then and you have some money, then you can say, let me buy some stock from Xilinx, for instance. And you should have. The first time I thought about buying some shares of Xilinx, this is more or less here at the beginning, it's 50%. Now in 5 years, it is tripled. So if I had the money then and I would have bought some stock from Xilinx, then it would already tripled, because now the stock is in about $150. And this is also partly due to the fact that Xilinx is also bought by one of the major players. It's bought a couple of months ago, but I will talk about this a little bit later. So if you look at the market share in region, then you see the most important region for FPGAs, buying FPGAs is Asia Pacific, then North America, and then Europe, and then you have the rest of the world. You can see in which it is used, mainly in telecom because of the high-speed capacity. Obviously, in industrial, automotive is looking more and more for their self-driving cars to FPGAs. Military and aerospace, I already mentioned why they use it. Data processing. You don't see a lot of FPGAs in consumer electronics. That's also the reason why it's not that well known, because it's more business or industrial component than it is found in your cell phone, for instance. Here you have an overview of the technology used. Now, this FPGA is a versatile component, can be anything, can have any hardware inside. So the configuration is stored somewhere in memory, and this is what it is where it is stored in the configuration. And the most used is SRAM, where you can store your zeros and ones in. And so that's why this is the biggest piece of pie of this cake. But we will talk about this a little bit later on how an FPGA is configured. Maybe you already know, but you have two major players in the FPGA market, which is Altera and Xilinx, but they are not independent anymore. Altera was bought by Intel a couple of years ago. And then this year, I think in October or November, Xilinx is bought by AMD. This is also the reason why the stocks went up as they did. So I put a small link here. If you, it's only quite recent when this was bought. But they are not the only ones producing FPGAs. You also have Lattice, Microsemi, QuickLogic, for instance. Acronix. Acronix is a special one because they don't use flip-flops. They don't use clocks. So there's only Acronix. So not no timed behavior. And then obviously you have ESAP, the one that I already showed you, the Brave FPGA. Okay, let's dive a little bit more into how an FPGA works. As I promised, people say it's a difficult component, but I will demystify the component. I'll make it easy. That's my goal. That's what I want to do. It's one of my life purposes to help people work with this component. So if you look at the logic function, you have something like this, quite well known: an AND gate, an OR gate, an XOR gate with American symbols. As you have logical variables, input variables, on which a logical function works, and then you have a certain behavior at the output variable. So a desired behavior can be translated in a logic circuit with logic gates. Now, if you have a circuit like this, then you can find the truth table. The truth table, you have all inputs variables, and then all different options for the input variables. And then you can see how the output variable behaves. So the behavior of this circuit can be put in a truth table. But also the other way around. If you have a truth table, you can build, or then you can have this logical circuit built. And this is important because this is how an FPGA works. If you have this desired behavior, you can put it in a truth table. But if you have this truth table, if you, for instance, had a hardware version of this truth table, then you could have this behavior of this logic circuit. And this is actually the core on how an FPGA works. An FPGA works not with logic gates, like the left-hand side, but it works with hardware truth tables, like the right-hand side. This is the core of how an FPGA works. It does not work with gates, it works with truth tables. So let me dive more into how an FPGA works. So if you look at the general overview on an FPGA, you always have the same. You have somewhere to have the logic, the gates, the truth tables. Then you have some wires to connect this logic block to this logic block. Maybe this one wants to talk to this one. So you need to have wires for signals, for data transfer. But obviously, this component cannot exist by itself. It will have some neighbors to talk to. So this is why you have this input-output blocks, input-output cells. So it should be able to talk to the outside world. And an FPGA cannot know what their neighbors will be. Today, the FPGA will talk USB. Tomorrow, it will talk I2C. Tomorrow, it will talk SPI. So these are different data protocols. So an FPGA should be able to talk to different neighbors. And he does not know what language the neighbor will talk. So that is why an FPGA needs to have on board all different languages from the start. So this was an overview of Altera. This is an overview from Xilinx. You have the same blocks. You have the logic blocks, programmable interconnects, which is programmable wires which can be connected to each other. And then you have the input-output blocks. So let us dive a little bit to the logic. If you go to the logic of an FPGA, both from Altera side as from Xilinx side, then you see something like this. So you have, this is the core of all FPGAs. So you have this 4-input lookup table. This is the truth table, but then a hardware version of the truth table, a lookup table. So you can look up the value of your output. So this is the combinatorial part, which does not use a clock. And then you have a sequential part, which is the D flip-flop. Any course on digital fundamentals, digital systems, will always have a combinatorial part in their topics. And then at a given moment, you go to the sequential part. So also how an FPGA is constituted is the same way. You have a combinatorial part and a sequential part. Now, if you go to the combinatorial part, then you have this hardware truth table, which is a lookup table. And actually, it is a memory array. So these are memories, memory cells, and it can store 1 bit. It can store a 0 or a 1. So this is the SRAM that I was talking about. And these are the input variables, but at the same time, these are the addresses of these memory locations. So if the address is 000, then this memory location is put to the output. If this is 001, then memory location 1 is put to the output. 010, then 2 is put to the output, and so on. From 0 to 7, you have the different addresses here. Let me give you an example. if we put a 0 here and all ones, then this lookup table will behave like a 3-input OR gate. Because an OR gate, if one or more of the inputs are a 1, then the output should be 1. Because if you put a 0 here and all ones, then you have a 3-input OR gate. If you put all zeros and a 1 here, then you have a 3-input AND gate, which means all the inputs should be 1, 1, 1, 1, which puts out memory location 7, which contains a 1 to the output. In all other cases, it is 0. So this is how you could build one logic gate, an OR gate, or an AND gate in this, depending on what is put in the memory locations. But any circuit with 3 inputs, for instance, an AND OR, you have this AND gate and an OR gate, any circuit with 3 inputs can be put in a lookup table. And this lookup table is then, so these zeros and ones are stored in these memory locations. Okay, the other part, so this is the lookup table, the memory, the SRAM memory, which can be addressed with input variables. And then you have this D flip-flop, which is actually to put the sequential logic in it. And what does it do? When it sees the clock flank, it puts out to the output the momentary input value. So if this is a 0, then it will put a 0 at the other side of the flip-flop. And the main difference is this output is made synchronous to the clock. So all flip-flops will put out their value at the same moment, which makes it easier for your processing, because then you know, then you have a stable output at the flip-flop. So this flip-flop is only used when a clock is used. When you use something in a clock structure, then you will address these flip-flops. Now, this is a quite important part because everything that you put in a clock structure will receive a flip-flop. And if you have big data structures like 32 bits, then you need 32 flip-flops. So you need a lot of them. Now, talking about this FPGA, you have about 20,000, a little bit more than 20,000 of these lookup tables, and you have the double amount of flip-flops. You have 40,000 flip-flops. So you see the importance that this is only recently that the people from Xilinx doubled the amount of flip-flops compared to the amount of lookup tables. So then let's look at the programmable interconnections. So these are wires that needs to be connected. So how can we connect wires? Like this, for instance, you have the upper piece of wire, the lower end of the wire. And if you put a 1 here, then they are connected. If you put a 0 here, then they are not connected. So again, you see an SRAM cell, right? So a cell that can store a 0 and a 1 to make this connection or not. Here, again, you have these SRAM cells. And when this is 0, 0, then data path 0 is connected to the outside. If it's 0, 1, then data path 1 is connected. Others, data 2 is connected. Otherwise, data 3 is connected, depending on the address put in the SRAM cells here. So again, these SRAM cells are not only used to put in your logic or to put, but also to make the connections. And this is also why these SRAM cells are needed. And then you can connect this wire to this wire, for instance, and these are just wires on your inside on your chip. And then if you look at the input-output blocks, you can see this is quite elaborate. And the reason being is that this input-output block, this is your translator to the outside world. So it has to talk a lot of different languages and have a lot of electrical parts to make sure that your chip is safe. or you can use pull-up or pull-down resistors and so on, or you can talk USB and so on. So this is why it is quite elaborate. But if you divide this difficult elaborate scheme, then you have a part which is an input part, then you have an output part, and then you have a three-state part. So this is actually how it is divided functionally. Again, you can configure this with SRAM. So again, you can place SRAM cells, and they are left out, but you can put zeros and ones to make sure that these elements are used. And how you use it, it is put in the IE configuration of the Xilinx XDC file from Xilinx. But we will look at that a little bit later on. Now, this was a simple representation of what is in an FPGA. So you have in an FPGA this logic, you have wires to connect the logic, and then you have the input-output blocks. But there are more elements in the FPGA. So you see, for instance, this DCM. This is a digital clock manager. You have block RAM, which is local memory in blocks. And then you have multiplier blocks. These are, for instance, what is also in an FPGA. Now, if we go more to the FPGA of this board, then you see the main part are these slices. A slice is a group of hardware put together, 5,200 slices, and each slice contains 4 lookup tables and 8 flip-flops. That's how I came to 20,000 lookup tables and 40,000 flip-flops. And then you have this distributed RAM, which means, as you know, these lookup tables, they are memory locations, so you can also use them as memory. That's why you have this distributed RAM here. Then you have some other elements. So you have a maximum I/O count of 250. That's what I told you at the beginning, that an FPGA will have a massive I/O count. And so maximum 250 for this type of FPGA. And then you have the other extra hardware put there. So like the DSP slices, this is for digital signal processing, obviously. Block RAM. CMTs or clock management tiles. These are for clocking purposes. PCI Express port, only one. GTPs are gigabit transceiver pairs for fast communication. And this is also something recent in FPGAs, that they add internal analog to digital conversion. In the older FPGAs, you always needed an extra ADC chip, but now these are also, you also have one in your FPGA. So, which is this extra hardware in a DCM or a CMT, a clock management tile of digital clock manager? What does it do? It can provide different frequencies. It can do phase shifting. It can eliminate clock skew because you have this clock that you put out, then it goes through your complete FPGA, and then you get feedback, and then you can make sure that the input clock is aligned neatly with your feedback clock. So that's actually what it does. To make sure that all the flip-flops, all these 40,000 flip-flops, that they see the same clock flank at the same time, which is a challenge. An FPGA is, this chip is quite big. So especially, it's not that big, it's just like 1 centimeter or something like that. But in terms of fast clocks, this is quite big because the clock needs to be distributed among these 40,000 flip-flops. So for local memory, you have this block RAM that you can use in different ways. And then you also have this multiplier. This is actually for DSP functions. Now, this is from an old chip, because we will talk about the multipliers in the new chip, in this Artix chip in the future, because they have a lot of these multipliers available. As I already mentioned, the clock distribution is quite important because a flip-flop here should see the same flank as a flip-flop here. And this is the reason why the clock is distributed in a tree-like structure. So it is first put centrally and then it is distributed. So the data path from here to there has the same length more or less than the data path from here to here. This is why it is it is laid out like that. And it also gets extra buffering. So you can put your clock on different inputs and it receives an extra buffer to make sure that the clock signal is stable throughout your FPGA. This is an important part. So now we know how an FPGA works. We know that it works with SRAM, that it has memory locations where you could put zeros and ones, and this will build your hardware. And this is a strong part of your FPGA, that you can build hardware. From existing hardware in your FPGA, you can build hardware to act according to your desires. So the question is, where does this bit file come from? Where does this bits come from? Well, they in this case of this board, it can come from 3 locations. Most of the time, we work with a small USB gate, and we use that to put your design files in your FPGA. So that's the third option. But you can also use this chip on the bottom side. It can hold your configuration file, or you can use the big USB port, this one here. So you can use the big one with a pen drive, a USB stick. You can put it in, and then it will get its configuration from the USB stick, which is an easy way. You can just put your FPGA somewhere in a field, put it in another stick, and it will do something else the next time. Okay, the important thing to note is that the amount of bits throughout your FPGA, so the amount of SRAM spots receiving a 0 and a 1, is always the same, because this is also hardware. It's not like in microcontrollers. If you write more code, then that you get a bigger program. This is not the case. The program to program an FPGA has always the same length, because the amount of zeros and ones spread throughout your FPGA is always the same. So this is why the memory chip is also always the same. It doesn't matter. It can always be the same memory chip, because you always need the same memory. Obviously, when you put a microcontroller in your FPGA where you will write your program for, then again, memory will become important. But for the configuration, it's always the same. So we're talking about this RTX 7 chip. It has 20,000 lookup tables, 40,000 D flip-flops. The question is, how should we address them? Because this will be very difficult. You cannot address all the 20,000 yourself. And so this is why we need VHDL. So now we go from what is actually in the hardware, in the FPGA, to how can we address this hardware. We use VHDL. And HDL is a hardware description language. It's used to describe hardware. And the V stands for very high-speed integrated circuit, which means you get very fast and integrated circuit. Now, if you work with an FPGA, you will notice that it is sometimes a little bit frustrating, because it takes a lot of time. When you start working with your FPGA, you made your design needs to be put in your FPGA. This process takes a lot of time. It is not that fast as a microcontroller system, where you can do trial and error. Change a piece of code, put them in a microcontroller. This goes very fast. With an FPGA, this does not go very fast. So a student might say, very high speed circuit, I don't think this FPGA is very high speed. No, but why it is called the very high speed integrated circuit is because of the fact that it is a tool, because of the fact that VHDL uses tools to develop the hardware for you. We don't need to address these 20,000 lookup tables. We don't need to address these 40,000 lookup tables. No, our programming, our programs, our software will do this for us. And that's why it's very high speed. It will develop a system quite fast. Let me give you an example which belongs to this circuit. So first of all, you have always this library declaration. Then you have the entity declaration. And an entity declaration actually states how your digital component is connected to the outside world, which is its interface to the outside world. In this case, you have an interface of 4 input switches, 0, 1, 2, 3, and 1 output LED, LED 0. So this is our interface. And then the architecture actually states what does it do? What does this digital component does inside your component or inside your FPGA. So this is actually the content. While the entity is the interface, is the empty package with pins on it, is this the content? What does it do? How does it behave? What hardware is inside your package? So this is the architecture. And in this case, we have an AND gate, an OR gate, this AND gate, and this OR gate, and it's XOR together at the end. And so this is actually how this works. When we start writing VHDL, we want to make sure that we can analyze the results. So there are 2 ways to analyze the results. You can use an RTL, which stands for register transfer logic. And this gives the logical buildup of your circuit, which means this gives to you an overview of how the tools interpret your text. You write some text, the result will be hardware, and the tools tell you, when I read your text, I think you want to build this. And that's how this RTL is used. You want to develop this. You want to make this kind of hardware. Now, the synthesized design, this is actually how your logical design is translated into FPGA hardware. It is translated to things which are readily available, which exist in your FPGA. So if you want to make this kind of logical circuit, we will use these elements of your FPGA to build this. So you find this in the tools under RTL analysis. You can make your schematic. Or under synthesized design, you can also open the schematic. And if you do this for this text, we wrote all the other things. They are made by the tools. And this is the only text that I needed to write to make sure that this works. So if this is translated in logic that we know, then luckily it is something that is very well, looks very much like this one. Right? It translates our piece of text in an AND gate, an OR gate, and an XOR gate, which is nice because this is what we want to build. Now, if we look at the schematic of the synthesized design, it will translate, obviously, not in gates, because I already told you an FPGA does not work with gates. It works with lookup tables, so it translates it into one lookup table. Your input signals are buffered. And always you have an input buffering, output buffering, which makes sure that the signals here are stable. Also that these signals are stabilized, that your input logic does not affect too much the input signals, and also here that these things are made stable and so on. So we always have some buffering, a lookup table, and output buffering. Okay, so if we dive a bit deeper into VHDL programming, then you see that you have three methods of designing. You have data flow design, behavioral design, and structural design. Now, the first one, data flow design, is the most simple one. It's just about gates and connecting wires. And this is data flow design. Behavioral design is actually the design like writing software code. And structural design is putting components together for a structural design. Simple components to make systems. So the first one is wires and gates, which is nice, which I already showed you. This is data flow design. It's just some gates and some wires connecting to each other, and some gates, some wires. That's actually what is data flow design. Which is nice for simple designs, but it will become increasingly difficult for complex functions. But any design will still have some data flow elements in it. It will become difficult to understand. Let me show you with this example. This is a multiplexer. And what does a multiplexer do? You already saw one, but it has address. And this, the data paths, D0 to 3, are connected to the output depending on the address. If the address is 0, then data path 0 is put to the output. If the address is 1, then 1 is put, 2, and 3. So depending on the address, one of the data paths is connected to the output. Now you can easily do this in VHDL this way. Z is not address 1, not address 0, and D0, or not address 1 and address 0 and D1, and so on. So you can easily write it like this. You see that is for only 4 data bits, 2 address bits, it is becoming increasingly difficult or increasingly complicated to understand. If you have some knowledge about digital systems, then maybe you will still regard this as being a multiplexer. You can find this, but if you don't have any knowledge, then this is just a difficult and long statement in VHDL. So this is why behavioral design comes in. Behavioral design makes it easier to read, makes it more human readable text that you can decide on how this works. So we have processes in which we can use statements like if then else constructions, which are very well known for people that do programming, or case structures, or loops, for loops, and so on. And so this can be used in processes. For instance, same example of the multiplexer. If you look at this one, you have a process, and then you have a case structure. Case, the address is, end case, end process. And so this is how the syntax goes. So case, the address is, when the address is 0, we connect D0 to the output. When the address is 1, we connect D1 to the output. When it is 2, we connect D2 to the output. When it's 3, we connect D3 to the output. As you can see, this case structure is very easy to read. It's much easier to read than this. If the address is 0, if the address is 1, if the address is 2, if the address is 3. Very straightforward, very easy to read. So this is the power of behavioral design. It's important to note that behind the process, you have these brackets, and it has this list. It has a list of input signals that can trigger the process, or the process needs to be evaluated again, either when D changes, when D changes, for instance, from 0 to 1, and the address is 0, then your output will change. This is why D can start this process. but also the address can start this process because of the fact if we change the address, then another data path should be connected. So this is the sensitivity list. In the sensitivity list, only input signals, no output signals, it's not needed. Only input signals from the ones that can trigger the process. Okay, so if we put this process and we look at the RTL, because we always want to analyze our design, then you see the tools tell us that we're building a MUX, a multiplexer, which is a good thing because that's what we wanted to build with an address and with data inputs. If we translate this to a hardware inside your FPGA, then obviously you get a lookup table. And maybe we should have thought that we got something else, but the biggest lookup tables inside your RTX 7 are 6 input lookup tables. So any structure or any logical structure with 6 inputs, you can put in one lookup table. And this is what is done. So we have the addresses and the data, and they are put in one lookup table. So we only need one for making this work. This is changed. For instance, if you use the old FPGAs, the Spartan 3E, for instance, which was on the Basis 2 board, they only had 4 input lookup tables, which then we needed 2 lookup tables to make this work. But as you can see, the main advantage of making simple designs in an FPGA is that we really understand what is happening inside. If you make simple designs first, then students will really understand how this FPGA is working. Okay, and next very important part about working with FPGAs is your simulation. So the question is, how do we test the design? Most of the time, we put a design inside your FPGA and we start playing around with these switches. Right? We take some switches and we see what the LED do. And that's what we do. So we implement the hardware on the FPGA board and we test all input options. This process can be automated in a test bench. And why should we do this? Because the synthesis, as I already mentioned in the very high-speed integrated circuit, synthesis takes time. Synthesis, the translation of your code into hardware, which exists in the FPGA, it consumes a lot of time. It can even consume hours. Sometimes a designer only starts his synthesis at the end of his working day because he knows it will take 3, 4, 5 hours to synthesize. So this is also the reason why you need to simulate first, test everything in the tools before you build your hardware. And so this is actually why you need to simulate first, synthesize later. So and how do we do this? We do this with the test bench. This is our digital component, the one that we want to test. And what we want to do, we want to test all different input or relevant input configurations. And then we want to see what does the internal component do with it? Or how does the input, changing of the input affects the changing of the outputs? And so what we do, we write a test bench around our unit under test, and the TUIT unit under test. We develop a test bench around this one, and then we see what the output will look like. Let me give an example on how this looks like. So we made a very, very simple design. We have input switches, 3 of them, switch 3, 2, 1, 0. We have output LEDs, 3, 2, 1, 0. And we just connect the switches to the LEDs. So the LEDs, if you look at the simulation, the LEDs, they just follow neatly the switches. If switch 0 changes, the LED changes. If switch 1 changes, LED 1 changes, and so on. So this is actually, so now we can see that it works as it should. Now, if we go deeper inside, if we implement this design, actually what we're doing, we are connecting 4 switches to 4 LEDs, which means that we are developing, we're using our FPGA as 4 wires. Now we are misusing our FPGA as 4 wires. We know that we have these programmable interconnections inside, but these are expensive wires, just to be short. But you can even look inside your FPGA when you implemented the design. You can look inside your FPGA and you can look at the individual wires. Now I selected all 4 of them, but you have input switches and then you have output LEDs. And these are the wires that are used somewhere at the border of your chip. Now these wires, they have a certain length. So this too will have its effect. So if we do this test benching, but we do this post-implementation timing simulation, then these length of these wires will be taken into account, which can become important if you want to have really demanding applications, because then the length of your data paths will not be will become increasingly important. And this relates to these abstraction levels. So if you do a normal simulation, we don't take into account the length of the wires. We can only take them into account the moment we know which wires that we're using. If you have more information, if you're more down the ladder of the abstraction level, if you have more information on how the design will be built. So, but we don't need all this information up front. Maybe later on, when we start, maybe we want to put our design in the FPGA, then this will become important. So I made a detail on how this timing simulation can be simulated. So you see, these are the timings that you have from your 3 wires. And you see that wire 0, 2, and 3 are more or less the same length, but wire 1 has a longer length. That's this one. You have one which is quite long compared to the other ones. So you can even see this in your timing behavior. And if you look at the difference in length, it's just a fraction of a nanosecond, which is not a lot, obviously. But maybe if you have a fast clock, then these differences can become important. This is where your input changes. This is where your output changes. So your input changes at 200 nanoseconds. Your output only changes after 4 nanoseconds. And it also even has an intermediate value of 0. And you have 1, 0, 2. So you have an intermediate value. An intermediate. Yes, you can. Wait, is there a question or something?
Oh, sorry.
Yeah, if there is a question, you can always ask, obviously, or you can put them in the chat. I'm glad to answer any questions if they are there. So in any case, your input changed at 200 nanoseconds. Your output finally changed at 4 nanoseconds later. If you know that we're using on this FPGA, we're using a 100 megahertz clock. This means that you have a period of 10 nanoseconds. So you obviously already see that the 4 nanoseconds is more or less in the same range. And so it will become, if you would, for instance, increase your clock speed to 200 megahertz, then your period will be 5 nanoseconds. Then you can see that they are already you can get into trouble if you want to have a fast design. So it's important to take these kind of things into account. Okay, so now we know more or less all conditions to start designing. We know how the hardware works inside, what is inside, that we will be using VHDL to develop our designs. And now we also know that we have some analytical tools to make an analysis of your design, that we do simulation to make sure that we make the proper design. So now we can start designing. I gave you one typical example. For instance, this 7-segment decoder. This one is quite straightforward. As you can see, it works with active low. So you need zeros to make sure that this 3.3 volts activates one of these 4 7-segment displays. And then you also need zeros to light up one of the LEDs which are inside. So everything is active low. Obviously, you want to steer these anodes to make sure that you can make different numbers on different parts of this 7-segment display. Okay, so what you need to remember for all eternity, if you want to make a decoder, if you want to make an encoder, you can always use a case structure. Case structure always works. And so that's also something I tell my students. If you don't know how to do this encoder, then you always should use a case structure because it always works. Case, when you send a 0, then this should display a 0, which means only G should not be on. So this is what you see. G is not on, all rest is on. If you see 8, obviously everything is on. If you want to have a 1, only B and C should be on, all the rest should be off, and so on. So you can make all your different numbers as such. And this is your test bench. So this is the component, your unit under test that you want to test. This is your unit under test connected to the signals, and then you do a loop. You just look at all different input options, and then you get something like this. So all input options from all zeros to all ones, and then you can easily look to this table that you get the proper output. So this is obviously the right output belonging to the right input. So this is a typical example. Another example why we would like to use combinatorial logic is for arithmetic designs, and this is important. So you need, for instance, if you want to use an FPGA where it is used most of the time, you will need some arithmetic options, and this is it obviously has also hardware to do these calculations. So if you look at a binary addition, this is some basic on binary addition. So if you add a 0 to a 0, you get 0. If you add 0 to a 1, you get 1. 1 to 0, you get 1. 1 plus 1 is 1. Is a 0 with a carry to the next one. And if you have 3 of them, then you have a 1 and a carry. This is how it works. This is how the decimal addition works. This is how the binary addition works. If you have something more than 1, for instance 2, then you have a carry. So what you want to build is hardware that can do this operation. So if we in your course Digital Fundamentals, you will find something like this, a half adder or a full adder. With we want to add bit A to B, and we have maybe you have a carry in that we also want to add. So 0 to 1 is 1, 1 to 0 is 1, 1 to 1 is 0 with the carry. And then if you have a carry in, then 1 plus 0 plus 0, you have 1. 1 plus 0 plus 1 is 0 with the carry, and so on. So you get this truth table. And then you can translate this into this circuitry. Because if you look at the sum, this is an XOR gate. This is this XOR gate. If you look at the carry out, then this is an AND gate. Right? So a half adder is always an XOR and an AND gate. And then for the full adder, if you want to add this carry in, then you get another XOR gate and another AND gate, and then you can add them together, because a carry out can be produced from this side or from this side. So this is how we would build this one inside in an ASIC. Now for an FPGA, they provided some additional hardware. Again, we know how an FPGA works. This is our lookup table, and these are our flip-flops. One lookup table, two flip-flops. Now, in between our lookup table and our flip-flops, you have this arithmetic chain, which can be used to implement arithmetic solutions. So this is the carry chain. So this is to do math operations. Because math operations are that important, obviously extra hardware is foreseen, and it is foreseen between the lookup tables and the flip-flops to do this design. If you look at it a little bit more closely, so this is again is your lookup table. This is your arithmetic chain, and then you have another XOR gate. And so you have an XOR gate, that is this one. The other one you can build here to implement this one. So in between, you have this carry chain. And it works. So this is your sum with the XOR gate and the other XOR gate. And this produces the proper carry in and carry out. For instance, if this is 0, 0, then this multiplexer receives address 0, which means that A is your carry out. A is 0, so carry out is 0. If one of these inputs is just 0, then you will not produce a carry out. If both of them are 1, then again this XOR gate gives 0, but you need a carry out, so the carry out is A. Because this can only produce a 0 when both of them are 1. So which means that the A is put as a carry out. In other cases, when this is 1 or only this one is a 1, then you get the address of this multiplexer is 1, and then it is a carry in which produces a carry out. If one of them is 1 and carry in is 1, then you get a carry out of 1, and so on. It's just to prove that this is quite an efficient implementation for making additions. Now, we don't need to bother too much. If we just write something like this, the sum is A internal, B internal plus C internal. And so you add things together. You add A, B, and carry in together. Then you get something like this. If we look at the synthesized design, then you see you use lookup tables, which contains this this XOR gate. This is for the lower bits of A, and then you use your carry chain. So in your synthesized design, you can see that you will be using your carry chain. This is for the upper 4 most significant bit and the carry chain, and then the final carry chain is for your carry in that we add. Voila. And if you implement this one, then you can look inside your FPGA again, as we did with the 4 wires. We can always look inside your FPGA which hardware is used. So if we zoom a little bit in, we see that there is hardware used there. So here you can see carry chain 0, carry chain 1, carry chain 2, and then your lookup tables. So again, everything will prove to be used. So this is your carry chain, and it is selected because we're using it because we did an addition. So this is an extra piece of additional internal hardware of your FPGA. And now you know how to use it. So a more complicated arithmetic function is the multiplication. So if we multiply 2 binary words, then this means that you write down either A2, A1, A0, write it down if B0 is a 1, or write only zeros when this is a 0. So write down, and then you shift to the left, which means you multiply by 2, and you shift again to the right, to the left. I mean, that's when you multiply by 4. So this is multiplied by 4, this is by 2, and this is not multiplied, or only multiplied by 1. And then you have to add everything together. So this is how a multiplication fundamentally works. So what you need is something to do in addition, and you need some AND gates to make sure that your number that you want to multiply, that it is put through or not. So if we put this in a matrix structure, then you see you need AND gates and you need adders. Half adder, full adder, half adder. So FA is full adder, HA is half adder. And it depends on this number. If x3, x2, x1, x0 is either zeros here behind the AND gates, or the value of x3, x2, x1, x0, if all y zeros are ones, then it's put through or not. So this is how it works. This is also the reason why we have this additional AND gates here. This is for implementing multiplications. So it's quite easy to do. M is the multiplication from A and B. So you can write just one piece of code, and this is your output. As I already told you in the beginning, VHDL, very high-speed integrated circuit. This is how I would like to emphasize this fact. You write one line of code, very easy. M is A multiplied by B. And this is your very high-speed integrated circuit. So you write one piece of code, and the tools develop this for you. And so this is, you don't have to bother too much on all the wires that you need to connect, all the lookup tables that you have to put zeros and ones in it. If you want to use a carry chain or not, everything is done for you. And this is then the test bench. So you see 3 multiplied by 0 gives 0, 3 multiplied by 1 gives 3, 3 multiplied by 2 gives 6, 3 multiplied by 3 gives 9, 12, 15. 3 multiplied by 6 gives 18. So this one stands for 16, and this 2, you should add this 2 by this 16, because this is obviously binary. So you have to think a little bit binary. Okay, this is an easy one. 4 inputs, 4 bits input A, 4 bits input B. Let's make it 8-bit. It's quite easy. Just change your input values. And this is your multiplication. So very high-speed integrated circuit. That's clear. And so this is just with one line of code. you get this amount of hardware developed for you. But something strange happens. If you implement this, then the tools will give you a warning that you're using too much power, 40 watts, which is a lot. These small spots over your head, halogen spots, it's called, they are about 40 watts. So for a chip, this is too much. The reason being is that you don't give any, normally you would multiply just a number of bits with a number of bits, but you did not give any clocking information. So it depends, it takes the worst case scenario. If you give these numbers very fast, so your dynamic power usage is very high. If you put them, if you would put these calculations very fast, then your device would heat up very fast because it does not know it. It takes its worst case scenario. Now there's also a way to do this more sufficient, because we know that inside your FPGA you have these multiplication blocks, you have these multipliers, so you better use them. So what you can do, you can use your IP, you can use multiplication by 8 bits by 8 bits easily, because they exist. And you see this component only wants to do this multiplication by a given clock, so it knows how much dynamic power it will consume. So it's quite easy to implement. You can just use some IP, which is readily available in your tools, and you can just put them in as a component, and then you get something like this. So you get a black box where you, and if you click on the plus sign, then you can look inside, and then you can see it's an invert DSP region, DSP48E, which means that you're using the DSP, the digital signal processing hardware of your FPGA to build this multiplier, which is a good thing, because this is hardware which is dedicated to do multiplications. So you can build this in the existing hardware, but you can also use the dedicated hardware, especially for multiplications. And again, we can look at our implementation. We can look more in detail, and then you can see that you have this big block. This big block is mainly used for multiplications. Remember this name, DSP48E1, because we will see this one later. This is especially, these are the blocks that are used for DSP operations. And this is why ESA also, or why space applications are using FPGAs, mainly to do some signal processing, which is important. You can see the power reduced massively. It's only 100 milliwatts compared to the 40 watts that we had earlier. So this is more effective on power consumption. And then you can see again how it's distributed. The dynamic power reduced massively, because now you know that you're using a clock, and this clock is 100 megahertz, and so on and so on. So this is why it is reduced so much. Okay, up until now we were looking at typical combinatorial designs where you use multiplexers, demultiplexers, encoders, decoders, and mathematical operations. These are typical combinatorial designs. Now for the sequential designs, which is also quite important, then we are starting to use the clock. We did not use the clock until now, while all the designs that you will find on the internet on VHDL will use clocking. So we enter the domain of sequential logic, which means the state of your system is not only dependent on a number of independent inputs, and you have a number of independent inputs and it gives a certain output. No, now the state of the system is not only dependent on the inputs, but also on the current state of your system. Given an easy example, if you have, for instance, a counter, if the counter is in the state 0, the next state will be 1. If you're in a state 1, the next state will be 2, and so on. So it depends on in which state that you are in currently. So this is why this, you have this sequential logic. Sequential logic typically uses these flip-flops, these 1-bit memory elements. And as I already told you, there are in each FPGA, there are 40,000 flip-flops, so they are sufficient to use. So a flip-flop is a 1-bit memory element. So it's the base element of all sequential circuits. And the amount of flip-flops is determined by the amount of states. If you have one lamp going on and off, you can use 1 flip-flop. If you have a 4-bit binary counter, you need 4 flip-flops. So let's build 1 flip-flop. It's quite easy. As I told you, as soon as we start using the clock, then flip-flops will be used. If we have a clock structure, which always looks more or less like this, if rising edge clock, then something happens. All signals that get assigned in this structure, all signals that get inside in this structure will receive a flip-flop. If D is 4 bits wide, then you get 4 flip-flops. But in this case, D is only 1 signal, so you get 1 flip-flop. This is how it works. So quite easy. So this is your RTL, your register transfer logic. So your design is translated into a clock, a data input, and then a clear, because we're using a clear. And then if we translate this into, if we synthesize this, then it's translated into the hardware elements available for you in your FPGA. Then you see you're using one of the 40,000 flip-flops. You have 40,000 flip-flops, you are using one of them. Again, input signals are buffered, output signal is buffered. And as I already told you, this is a clock. We're using the clock for the first time. As I told you, the clock is always buffered twice. It is buffered at the entrance, at the input output pin, but it is also buffered again to distribute your clocking among all your flip-flops. Because this line should be the same, or the flank on this line should be the same for all flip-flops in your design. So flip-flops are called registers in your tools. So you're using 1 out of the 41,600. So and you're using 4 I/O pins of the 106 available, and so on. So this is, and you're using 1 clocking of the 32 clock structures available inside your FPGA. Okay, so this is for 1 flip-flop. If we make our input 4 bits wide, like this, you just make the same clocking structure, but you add load if you want. You don't need to add load, but you can add load. But what will happen? You get 4 flip-flops in your RTL design. You get 4 flip-flops in your synthesized design. 4 out of the 41,000 flip-flops. If you want to make a shift register, which means the data of the one flip-flop is connected to the data of the other one. So this is something, it's also used a lot in DSP operations, because you will sample, you will take different samples and process them and delay them with the clock. So this is also something that is done often. So the flip-flop is of the one carries the data to the other one, and so on. And this can also be 8 wide to 8 wide to 8 wide. This is also a possibility, because that's something that we will. Now we use only one data input, but you can also have a broad data input. This is also possible. So if we if we want to develop something like this, again, clock event and clock is 1 or rising edge clock, it does the same. It is actually the same. The data in the 1 bit goes to the first register, and then what is available in 3, 2, 1 shifts to 2, 1, 0. So what is available in 3, 2, 1 goes to 2, 1, 0. And so this is how a shift register works. You see the output of the 1 register goes to the input of the next one. And so this is, and then you can put everything outside for your reference. And again, in the synthesized design, you get more or less the same. Okay, so I don't want to go too deep. I have foreseen for my courses on FPGA, I have all the examples ranging for all the difficult topics or all the difficult different things that you would like to develop. And then we obviously want to develop some kind of system. So we have all combinatorial designs, and then we have all the sequential designs, and then we want to build them together to a system. So this is, for instance, such a system. This is a small arithmetic logical unit. Logical, it's a small arithmetic unit, because you can do an addition of 4 bits, a subtraction of 4 bits, and a multiplication of 4 bits. Because I already showed you how we can make these different components to make sure that they work. We have a demultiplexer and a multiplexer. So you can decide either we add 4 bits to 4 bits, we multiply we subtract 4 bits from 4 bits, or we multiply. And the decision to do one of these, you do this with this addressing of the muxes, which means that here you have your instructions. If you look to the data sheets of a microprocessor, then you get a couple of pages of instructions and what the different instructions does. So here you can see a very simple processing unit, and it can do 3 things. Very simple, but in any case, this is the core on how a microcontroller will work on the ALU side. And then you have the register, so you can put, with only 4 bits, you can store them, some of the value here, and then add an additional 4 bits, and then you can work with these 4 bits. But if you would look inside, there are a number of movie clips in this. If you would look inside your microcontroller, then you will find comparable things. So this is, as I already told you, we have this very high-speed integrated circuit. Only in 1.5 hours of presentation, we managed to get a decent idea on how to build a microcontroller system on an FPGA. Another typical example is to make a stopwatch. So you can do start, stop, reset, and you can build it like this one. So this will count for the ones, this will count for the zeros, and then you can put them out. This stopwatch will count from 0 to 999, and then again to 0. That's what happens with this stopwatch. You see again the clock. We need to have a decent divider, because we need to go from 100 megahertz to 1 hertz clock, and we make a divider to make a 100 hertz clock. And this 100 hertz clock will be used to switch between ones and tens, and to switch so fast that our eyes cannot see that it is switching between the two. So that is why we use 100 hertz, because the capacity of our eyes is about 25 hertz. Right? So if you have a clock at 100 hertz, it will switch between the two this fast that we cannot see this. But this is where we want to go. We want to go from very basic understanding on how to build these different components, and then we build a system. So this is actually how we come to structural design. And structural design means that we're building small components, we test our components, and then we build them together to systems. This is a very important lesson for my students, that they actually, digital systems design means developing easy parts and then building them together to make more difficult and elaborate designs. And so this is, I think, quite an important lesson to take away for my students always. So this is because you can test all these small components together and then make a bigger design. Now, another system can be, for instance, this system. Right? As I already explained you, we can build anything in an FPGA. So the tools provide you with microcontrollers. You can just have an 8-bit, this is 32-bit microblaze. You have the PicoBlaze, which is an 8-bit microcontroller. The microblaze is a 32-bit microcontroller that you can put in your FPGA and build a complete system. So you have USB interface here. You have a 7-segment interface here. You have something for your bus structure and so on, local memory interfaces and so on. And then you have a centrally located microblaze system. So you can also use an FPGA, for instance, to teach computer architecture. You can do this, but which is also possible you can also get an ARM microcontroller, which is quite well known, an ARM microcontroller, powerful microcontroller, and you can also get the VHDL code for this one, or you can buy it in an IP that you cannot look inside, but you can use it in your designs in an FPGA, which is done often. And you have this new MacBook Pro from Apple, which uses an ARM microcontroller. So it's not something, this ARM microcontroller is not something that's only used in microcontroller systems or in IoT systems, though it is actually used in the newest laptop from Apple. So it's not just an arbitrary microcontroller. In any case, you can use an ARM microcontroller, use it as an IP, and build your system around this one. You even have, I also have this one here somewhere lying around. You even have FPGAs that already have this one. You also have an FPGA where you have an ARM microcontroller which is already embedded inside. So this is Zinc is called. Zinc is actually hardware, which FPGA hardware with a hardware microcontroller, an ARM microcontroller in it, or even two. So because Xilinx, they noticed that a lot of people, they are developing systems right away with microcontroller in it, so they decided that it would be a good thing to provide their customers with a hardware, microcontroller hardware inside. Okay, so this is how an FPGA works inside, how you can go from easy designs into small systems to elaborate systems. Now we know how it works. Now the question is, how can we make sure that it also works in space? Now, the problems for FPGAs are the same for all microcontroller systems, but it has some additional problems too. So here you have some general problems that you, or difficulties, challenges that you might face when going to space, being mechanical loads, outgassing, electrostatic discharge, atomic oxygen, temperature fluctuations, the problems of vacuum, micrometeoroids, and space debris and radiation. So if you look at space environment, it is indeed a challenge to get something working out in space. Here you have an overview of all space environment things that you could encounter and which effects that you might have. But let me look a little bit deeper into the things, especially for FPGAs. But first, we look at the different things that might occur on a satellite, for instance. Here you have some effects, which is quite interesting for us, is this one, the single event effects. When you flip, for instance, a 1 into a 0. As I explained in the beginning of my presentation, the configuration, how an FPGA works, is stored in zeros and ones. What might happen if you change one of these ones and zeros to, if you flip them, you change your configuration. This means that maybe a certain data path is not connected anymore to another data path which is needed. So this is quite important in FPGAs, that you should always have the same configuration bits available, because also if you change something in the lookup table, if you change something in your how flip-flop is configured, this will change completely your hardware. So this is an important topic. So getting your microelectronics to space, obviously you have mechanical loads, which is important to take into account. Obviously, during liftoff, you have a lot of G's that you should withstand, and you have some shock when you have this explosion, when you lose your lifting rockets and so on. So these are things that should be taken into account. You have a certain mechanical stress that you will have, but also in orbit. If you go from very warm to very cold through when you pass around the Earth, that too will have its effect on the mechanical loads. Outgassing. So if you use things, glues and so on, these glues will outgas, which means that you could have this gas giving deposit on your optical devices, so that you cannot use your star tracker anymore, or that you cannot use your lens for your camera anymore. But you could also have an artificial atmosphere, because normally you take into account that you don't have an atmosphere in your satellite, but then you will have an atmosphere which maybe can conduct heat in a way that was not expected or calculated. And so this is can be a problem. Obviously, electrostatic discharge can range up to 20 kilovolts. We know electrostatical discharge can be hazardous for all electrical components. This is why they come in these special bags like this one, so that they are not charged when they get outside this bag. And so this is the same for your satellites. Atomic oxygen, which means oxygen which is not in the configuration of O2, but only O1. And O1 is very reactive, so it wants to react with all other chemical substances. So that's the reason why it can cause damage, corrosion, and so on. Temperature fluctuations. You have the warm side of the Earth, the cold side of the Earth. So this can have its effects. Also, vacuum can have its effects on whiskering, so that you have this metal whiskers. And so here you see them. And so these are whiskers these are actually the hairs of the cat. The mustache of the cat is the whiskers. So whiskering means that you have these small hairs growing from your soldering paste. So here you see them again, and they can cause short circuits and so on. Sometimes they just burn away and nothing happens, but they can also. There is the story of a very expensive satellite, and they malfunctioned due to zinc whiskering. Obviously, you have this micrometeors and space debris, which is just small items floating around in orbit. So this is can be hazardous for your mission too. Then you have cosmic rays, so radiation coming from cosmic rays, solar flares, solar wind, or coronal mass ejection. So these are actually ionized particles, protons, alpha and beta particles that can affect. And this is very, this should be taken into account when using microelectronics in space. So a lot of these particles are stored, are floating around in the Van Allen belts. These are the belts with high radiation levels. So you have the inner Van Allen belts, the outer Van Allen belts. So you have to take them into account. And these are the effects that you could have from radiation. So lattice displacement, that's what happens here. So that you have a displaced atom in your lattice of your so in your matrix structure of your substance. So this can be have its effect. Total ionizing dose. This is something that worsens with age. So it is the aging of your components in space. And then you have your single event. So something happens, a particle flies inside your microelectronic and changes. So you have here your CMOS transistor, and a particle, fast-moving particle, changes the way it behaves. And then your effect can be more or less hazardous. And so you have a latcher, which means changing a 0 to a 1 or something, or transient is something that is passed through the data wires, or an upset. But if you have a burnout or a rupture of your gate, then your microelectronics are gone. Now, this is a complete set of specialty to develop this kind of to develop microelectronics that can withstand radiation. So I used to work with a professor here in Belgium that also developed the microelectronics for the CERN in Swiss. So there you have this particle accelerator. So for simulating Big Bang things and like that, looking at the origin or how everything is structured in how everything is structured in materials and so on. So you have a lot of reasons why you can get radiation, which can affect your how it works. So you also have a lot of mitigation strategies. So here again, you have this different things that can happen. This is an SRAM cell, for instance. This SRAM cell, if it changes to a 0 or to a 1, then your configuration will fail. Your FPGA configuration will fail. So this is, for instance, a transient which is transferred throughout. So you get maybe some data in your FPGA that is not data. So this is why it can be a problem. So these are things that can happen. You can use shielding, for instance, as mitigation. You can have an insulator here, so your radiation path is much less long. It's a smaller radiation path to your component. You can use shielding, for instance. That's what happened here. Or you can use triple module redundancy. You can just do a redundant structure of your design. So you can make it hardened by design, hardened by process, or you can just use more hardware and then vote what should be the output. So this is what I already told you. In an FPGA, the SRAM, the circuit itself is stored in RAM, which means if you change a lookup table, then your combinatorial function changes. Your I/O configuration can change, for instance, and it can cause an open connection or a short circuit. So these things are well possible if you flip these kind of things. So what do they do for this? This is actually how a D flip-flop is built, but a very simple one. And this is how you can build a dual interlocked storage cell. So you can make them interlocked so that you make sure that you have that if one of them gets affected by a particle, then the other ones are not. So this way you can make them more fail-safe. You can always check your configuration. Check again if your configuration is still valid, so that you can do this with this configuration memory integrity check. So these are things that you can do. You can also add some software error detection and correction that you want to do this. And so there's a number of hardware and software solutions that you can do, which are implemented obviously in this Brave FPGA. This is a big reprogrammable array for versatile environments. They use these different things for radiation hardening of their FPGA. So these are some examples. And so this is a normal standard RTL design. You have sequential logic, combinatorial logic, sequential logic, combinatorial logic. This is how it works. And then what you can do, you can, with the same combinatorial logic, you can feed three flip-flops or a number of flip-flops. And then you can make a majority voter, which one should be correct. If this is 0, 1, 1, then the correct will be 1. Right? Correct one will be 1. And then you could even have feedback and change this one to 1. Right? So that's something that you could do. Or you can even also make your combinatorial logic also 3 times. 3 times the same, and then 3 times a voter. And then you can, because obviously also your combinatorial logic can also be affected. And so this is why you can make this triple modular redundancy. So make them redundant, that you can make sure that that you can have the same hardware 3 times, and you vote for which is the best one. So you can do this local, you can do this distributed, you can do this global. Obviously, this comes with a price. The more you make things redundant, the more hardware that you're using. This is clear. And then still you have to make sure that you don't have one single point of failure. For instance, if you have this majority voter, you have only one majority voter, this one can malfunction too, obviously. And so it depends a little bit on the amount, because here you also have 3 voters. So it depends a little bit. You have to level out the amount of hardware that you want to use to make sure that you have make it stable. Because here too, you have 3 minority voters, so this is also 3 majority voters and then minority voters and so on. And you can have feedback to make sure that the ones that you chose, if this is 0, 1, 1, the majority voter says it is 1. Okay, let's make this faulty 0, make this 1, 2. And these are things that you can do and change the things that went wrong. You have a tool for this in Xilinx, right? The triple modular redundancy tool. So here you can find triple modular redundancy. You have all these tools that you can put them together in Xilinx. If you want to have more information about radiation hardening of your space electronics, you can look at this standard from ESA and this one, and this is specially voted or devoted to FPGA, because FPGAs are used a lot. And all these three are from ESA, and this is the one from NASA on how to use microelectronics and FPGAs in space. Okay, I still have some time left, which is a good thing, because I also wanted to show you, which is a very important part on FPGAs, is obviously the DSP part. As I told you, you have this camera looking at the stars to make sure that the satellite knows its position. Yeah, this calls for DSP applications. Let me have a sip of water. So, we need a DSP, and actually working with digital signal processing on FPGA, and actually working on this, it's always the same. It always has to do with filtering. If you have filtering, then we can have high frequency signals, low frequency signals, which can be used for digital signal processing, for edge detection, and so on and so on. But I do with my students, I use the DSP with this audio interface to make the high and low frequency, to make a digital mixer. And this is obviously because it's fun to do. But actually the principles behind this, you can also use them for a higher level things. My next phase will be to use this one. Also nice to use a camera for your DSP applications. But I always want to do things with my students which are rewarding for them. So with camera and with sound, that's always nice to do. So what did we do? We wanted to have our data transferred from this audio tool to our FPGA, and then apply some digital filters, and then transfer the data back to the speaker. Okay. So if we look at the DSP basics of such a thing, if we have, for instance, a microphone, then we use a filter. Then we use an analog to digital converter, and then we do this digital signal processing here. And then if you want to put it again to the outside world, we can have a speaker and a smoothing filter and so on. So actually what DSP is doing, digital signal processing, is replacing traditional analog with capacities, with capacitors and coils and so on, and resistors, but make them digital with the same effect. So it is used a lot. For instance, for speech processing, that's something that we know. We know that we can say hello Siri or hello Google or something like that. Sonar, radar, which are more things that we'll be using in space applications. And other sensor array processing, spectral density estimation, statistical signal processing. digital image processing, for instance, data compression. They all use DSP basics, video coding, audio coding, image compressing, and so on. So, but in general, it all boils down to the same things all over again. And it has to do with a lot of mathematics. So a good thing about this FPGA that we have this dedicated hardware to do mathematics, because this will help us to make stronger designs. So we have this produced for mobile devices, wearable smart cities, and so on and so on. These they are used a lot, these DSP functions. In our case, this is a slide from Xilinx, where you can use FPGAs and where you can use DSPs from your DSP functions on FPGAs. And for instance, wired communication, wireless communication, automotive infotainment, consumer electronics, audio video broadcast. As I already mentioned, they are used a lot of FPGAs, medical images, test and measurement, and obviously aerospace and defense. So this is why we are interested in these components. Now, it most of the time boils down to two types of filtering. You have the finite impulse response filtering and the infinite impulse response filtering. The finite means that you will have, if you have an impulse somewhere here, then at a given moment, this will die out here at the output. With the infinite, you can have the case that an impulse here will trigger an ongoing effect on the output, because we're using not only the inputs to calculate the output, no, we're also using the output to calculate the output. So this is recursion. So these are the two main filters that we will have. What is this? This is a sample with a number of bits wide, for instance, 8 bits wide. This is this sample delayed by 1 clock cycle. Same sample, another clock cycle. Same sample, another clock cycle. So you have different samples at different times. And obviously, if you want, for instance, look at how the frequency is changing, if you have a high frequency signal or a low frequency signal, then obviously you need to look at the sample at different times. And if it changes very rapidly, then we have a high frequency signal. If it changes slowly, then we have a low frequency signal. So these are not more than flip-flops, because we want to delay our signal. So these are flip-flops, these are registers. Now what we do with the sampled signal, and then the sampled signal delayed with one cycle, sample signal delayed with one other cycle, we multiply this sample with B0, B1, B2, Bn. And so we multiply them. So we will be needing multipliers. And then the result of this multiplication is added to each other. So we add the effect of the sample at that moment to calculate the sample, the output signal, but also the effect of the last sample and the effect of a sample of 2 clock cycles ago, the effect of 3 clock cycles ago, the effect of, and we add them together to calculate the sample at that moment. So this is how the convolution filter works. Here we do the same. We also will store the output at that moment, and we store them always 1 clock cycle. So the output does not only depends on the sample now and a couple of samples ago, but also the output of now the output of couple of samples ago. So this is recursion. So what do we need? We need registers, we need multiplications, and we need additions. Add to add to add, accumulate. That's what it's called. So this is the same. Registers, multiplications, and additions. So the output n is a multiplication of this factor with the sample now and the last samples some time ago. So that's what I told you. We need memory elements to work on different samples. And each sample gets a weight, a coefficient, with which the sample should be multiplied. And all these weighted samples should be added to each other. So the combination of a memory element and a multiplication, a coefficient, we call it a tap. And a tap gives an indication on how good the filter is built, or how the amount of filtering can be done. For a FIR filter, we have something like this. And this is the finite impulse. You have an impulse and it ends at a given moment. Here you have an impulse and it may not end at a given moment. It may start to oscillate or something like that. This can be possible in an infinite impulse response. It's not always the case, but it can be the case. Again, coefficients, the delayed samples, the input samples, the delayed output samples, and then you add them or you subtract them. And so this is how it's called. So this seems quite straightforward, and it is just a combination of registers, multiplications, and additions. So a filter tap is a delay coefficient delay pair. The number of the filters is an indication of the amount of memory required, obviously, how big your filter will be. The number of calculations needed and the amount of filtering that the filter can do. A MAC is a multiply accumulate, is typically something that we need. We need to multiply and add, multiply, add. So a MAC is something in the context of DSP, is something that is, for instance, put into a DSP processor. You have traditional programmable digital signal processings, and then processors, and then you have FPGAs. And so the advantage, you have a RISC computer with an additional MAC, because you can build this, you can build multipliers, you can build accumulators. And so this is built in this programmable digital signal processing. So the advantage is that you can do this quite fast because they're optimized for this. And also if you have a complicated algorithm with a lot of if then else constructions, then you can do this in programmable way. Now for an FPGA, your MAC in any case is more expensive than the one in your processor, but you can use it for high bandwidth signal processing applications. And so more for front-end sensor applications, you will use FPGAs. So here you can see why an FPGA can be used and what the advantage is. You have, in an FPGA, you have a number of DSP blocks, DSP48E. Remember, this one were the DSP blocks available in FPGA, while a conventional processor has only one MAC, and the MAC needs to be used a couple of times, 256 loops, to calculate your data output. In an FPGA, everything can be done parallel, everything at the same time. So this is the reason why an FPGA can be faster in DSP calculations than a traditional digital signal processing. It depends what you want, because you can also build the same structure. You can also build them in FPGA, and then you don't gain anything in speed. It depends on your application, obviously. Here again, the same idea. So if you have a DSP processor of 1 gigahertz, but you need to do 256 clock cycle, then you can do 4 mega samples per second. if you only have a slower FPGA, 500 megahertz, which is a fast FPGA, you will encounter a lot of difficulties if you want to use a 500 megahertz FPGA. In any case, it will be very challenging. But you can use 256 multiplications in parallel in one clock cycle, so you can do 500 megasamples per second. In theory, it will still be challenging. Should not underestimate this in any case. But again, you see this register appearing, all this in parallel multiplication on parallel accumulate. So this is how this is done. So you could decide, you can build the same and just do this feedback. Then you gain in area, or you can do a gain in speed. You can do anything in parallel. This is also possible. High speed, you have the 600 megasamples per second. You can do this semi-parallel, 300, or you can do this serial. So then you will get less data throughput. It depends on what you want to do. Okay, so now back to the sales pitch of Xilinx. If we look at the sales pitch, then you have this four, you have the Artix, the Kintex, and the Vertex. And then you look at the DSP slices. You can have 40 to 70 DSP slices, which a DSP slice is actually somewhere where you can do these calculations. You can see you can have more or even more. Now this is the sales slide of Xilinx. Let's look into the one that we are using, this XC7835T. You have 90 DSP slices. So building this cannot be done with our FPGA. You can go to a tap filter of 90 in parallel. 90 probably is already a lot in what you would like to have in parallel. But as I told you, the more taps, the better the filtering, and so on and so on. But you can do 90 in parallel with our FPGA. Now, for audio samples, it's not that important, because if you go for audio samples, we are talking about 96 kilohertz or something. So audio samples, you will not come into the limits of your FPGA with this one. Now, if we look to DSP, you will often find that they are talking about pipelining in DSP applications, because we want to have things quite fast. Now, then you need to know what pipelining is. Pipelining in microcontrollers means this. You have, for one instruction, you need to fetch the instruction, decode the instruction, execute, and write the instruction. And it takes you 4 clock cycles to process one instruction. Now, pipelining means that you start fetching the next instruction already with the next clock cycle. So this gives you a performance gain. So if you can do some instructions in parallel, this is what pipelining means in microcontrollers. Now, pipelining in digital logic is more or less the same. These combinatorial processes take time. If you want to do multiply, add action, multiply and add, maybe you can already start to multiply the next sample, and while you're still adding the former sample. This is why we put registers in between flip-flops. We put registers here, we put registers here, so you can pipeline everything. So you can put, because this will see a clock, this will see a clock, and the limitation on the clock frequency between this register and this register is the time needed for the multiplication. If the time needed for multiplication is 1 nanoseconds, then you can have a clock of 1 gigahertz. This is more or less how this will work. I have to check, that's something that's on my to-do list, how much time a multiplication in a DSP block will take. I have to check in the data sheets, but it would be a nice thing to have put it here. So it's a mental note for next time I do this presentation. In any case, if you put a register here, then your frequency can increase. This is also the reason why in the input-output block, you have these registers there. Because if you can clock in the data which is coming in from the neighbors of your FPGA, then again, you can increase the frequency. This is what pipelining means. Okay, now let us look a little bit more into detail what the DSP slice has. Clearly, it has a multiplication, and clearly it has something to an addition. So this is a small ALU, an arithmetic and logic unit, and this is only just multiplications. And in between, you have these pipelining registers. So this is how this works. And from this DSP 48 tiles, you have in total in our FPGA, you have 90 of them. So you can make a 90 tap filter from this. So, so you can use them in parallel if you want to have a high speed, or you can use one, only one. You can also use them just as additions. If you leave out the multiplications, you can use them as addition. But you have to take into account your pipelining registers and make sure that you need to add an extra here, because otherwise you will not be. You have to make sure that all data paths see the same amount of registers, because otherwise some of the data will be left behind one clock cycle, and that's not the idea, obviously. So you can use the FPGA in parallel with your DSP. So this is something that was done, as I showed you in the Brave, the Leon plus Brave calculation. So they use an FPGA as co-processing. And so a lot of effort is done with the vendors to make sure the data can shift fast between the processor and the FPGA. Now here you can see actually how this is done. And so we have we want to multiply this with the coefficient. So this is the sample, this is the coefficient, multiply them, and then add them. So multiplication, addition, it's always the same. So this is actually how you could implement this in HDL. So I have added some interesting YouTube movies for you to look at on how we can do this. And also I've added some examples in VHDL on how to build some filters. So this is a simple moving average filter on how you can do a moving average. I've added the VHDL files too, so that a moving average, but it does actually, it takes some samples of this high changing signals, and then it calculates the average of the past 8 samples. So actually this is some sort of low pass filter, because this fast moving signal is filtered out. This is what a moving average filter does. And I've added the VHDL files for this. A FIR filter, this is with separate coefficients. So that's also what I did, what I added in VHDL files. So these are the coefficients that we want to add. And depending on these coefficients, this will act as being a low pass or a high pass filter. So we generate different, we generate all these registers. That's what happens here. We multiply them and we add them, as you can see. And so actually, it always is more or less the same. You can also use some IP inside your Vivado. You can find this multiply and accumulate. Again, multiplication and addition. So it is not, TSP is quite an important part, but it's not that difficult to implement because you always find the same elements again. If you have this feedback, this infinite impulse response, then you have your forward feeding. Yeah, this does not, it does not look the same as here. Maybe I should change this. So this is B1, B012. This is A012. That's why I should switch them in between, but because this is the forward feeding coefficients, and these are the backward feeding coefficients. But in any case, in different states, you can add them together. You can multiply them. That's what happens here, and add them together, and then you can get this working. And this actually works because I did this a couple of weeks ago on the sound. So you can use different different coefficients to have a low pass or a high pass filter, and it works like a charm. I was quite pleased with this because it did not work from day one. So I had to do what I always tell my students. I have to think before I act. In any case, you have a lot of IP inside Vivado from Xilinx, where you can use different things for your DSP functions. So what I needed to do was to build this audio loop. The first thing that I wanted to do is to listen to my my music through the FPGA and just make a loop. Take the audio in, loop it inside, and send it outside. So later on, you can add filters, which I did in the next stage. I was quite pleased. My wife, she came in and I was saying, oh, I'm listening. I'm listening my music through an FPGA. She was not very impressed, but I was impressed by myself. So that's maybe the most important part at that time. So without the filters, we needed to make this, and what it does, it samples left and right channel, left channel and right channel. It samples it at a given sample rate. And so we need to make different clocks. We need to make a base clock, a master clock, and then the left-right clock to make sure that we sample left and right. I wanted to make something like this. So here you have the samples. So the sample comes in, the data comes in from this side. And then it is made parallel. So this is the sample, and this sample comes back in, and then I send out this, what happens. And I made some registers to make sure that we don't loop directly back, because maybe we only loop it back one clock cycle later. That's what is happening actually. But I have to say it did not work. So I put everything together and it did not work. And but that's because you have a lot of things that can go wrong. And maybe it does not see the samples, the data does not come in, and so on and so on. And so I had to find a solution. First thing that I did, obviously, was make a simulation, because that's the first thing. So in the simulation, everything worked fine. This is the sample clock. This is the master clock. This is the sample clock, and this is the left-right clock. So it seemed to work quite well. So this is the left-right sample clock, master clock. And so this seemed to work quite well. But still, I was not convinced that we had the right signals inside the FPGA. Luckily, you can build everything in an FPGA. So what you can also build in your FPGA, you can build an integrated logic analyzer, which gives you live data from the signals inside your FPGA. You can take one of the signals that you're building your system, and you can put them outside through your USB connection. So you have not simulated data, but real data from the data inside your FPGA. And this is what you want, because we want to know if the FPGA is seeing something or not. And so you can probe some of these input signals that I did. I put some bugs on it, so for the debugging. And then I got something like this. So here you see your actual input samples. This is my music. This is my left music. This is my right music. Left music, right music. And this is my actual music that I'm seeing. And this is the actual music after DSP that I'm sending out to my speaker. So this is a good thing that you can see actually real samples coming in and going out. Real time. Still did not work. So what I wanted to do, I wanted to check whether the signal really came here, right? That I really got the signal there. So I got an external logical analyzer, and then I got something like this for the one channel, and I got something mirrored for the other channel. So then I found out my mistake. So you have this these pins numbering, and it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But in chips, it often goes like this, and it makes a loop like this, a U-shaped loop. But now it was numbered like this, and this was my mistake. I mirrored the outputs. So actually I like to tell this story because I always say to my students that they need to test every step in between, and now I was the one that made the mistake by being too fast and not reading the data sheets properly, and so on and so on. I always say first read the data sheets, and I didn't do it myself. So that's a lesson learned for myself too. With this one, I would like to conclude my presentation. We covered a lot by first looking at the FPGA as being being a component and how the internal hardware works, more or less. Then we started how we can make simple designs, how we can make more elaborate designs, both combinatorial as sequential, to make systems. And one of the most used systems in FPGAs is a system to do digital signal processing. So we also covered that part more or less on how to make your first digital signal processing designs. And if you would like, if you buy this component and this component, it's not very expensive, then you can start doing your own audio processing with your students, which is very fun to do. So, and I will always help you if you get stuck somewhere. Okay, so this is it. It's a marathon of speaking.
Thank you very much, Big. There was some questions, if you could.
Yes.
So could you show us some tutorial, for example, like a Hello World on FPGA platform, like how to write program, upload to FPGA and use it in real?
Yeah.
And also, just addition, if it's possible, to provide software development tools for FPGA.
Mm-hmm. The software tools from Xilinx Vivado, they are free, so you can get them for free. And this Basis 3 board, it's also not that expensive. We bought a lot for our students so that people can have them. It's about $70 or something, which is it's more expensive than a microcontroller board, but you can use it for a very long period, because I've been using the predecessor from this one for 10 years now, and I only recently switched to this one, because the ideas behind, and the Arctic 7 is already quite an advanced FPGA. But the ideas, they stay the same, and there's a lot of resources inside. So students will never be able to fill the complete FPGA. With the old one version, students, they managed to get them to use all hardware, but with the Arctics, it's not possible. And you need to be a professor to make sure that to fill everything in your. But in any case, I have foreseen, and I will post them in our Dropbox. I've foreseen a complete tutorial on how to get started and how to get a project up and running, and it's self-explanatory.
Okay, thank you. And so, which software you told us that it's free? Can you
it's called Vivado.
How to type? Can you type it in a chat
yes.
or somewhere?
Let me have a look. I'm looking because while I'm presenting. Okay. In any case, I will quit the presentation. You can always contact me if you have some questions. But I will quit the presentation because that will be easier for me for typing something in the. Oh, how should I do this? Okay, here I am. So it's called Vivado. So and every year you have. Oh no, I'm. I've put him in the wrong place. This is the one that I needed. Sorry. Okay. Yeah, it's with different tools, different parts. Okay, so it's called Vivado, and you can use the Webpack version, and it is free. The people from Xilinx, they offer this free because they are producers of these chips and not from the software. Sometimes you notice it that they are not software developers in the free tools, but in any case it works. It works quite well, and it's getting better every time that you do so. So I have everything readily available. If you want to start with this component, then I would suggest. What I do for a couple of years now, I teach digital fundamentals just on basic gates and so on. I do this directly on an FPGA because this allows for students to really understand what is happening. If you make simple designs, then you really understand what is happening because you can analyze them. And later on, the tools will develop big designs for you, but then at least you know what's happening behind the screen.
And also, one of our researchers told that they have Thoracic DE0.
Yeah, that's a good one. I also had this one, and it's other tools, also free tools, also quite a cheaper version. This Thoracic. A very good board too, yes. And even cheaper than this one, I think. And it also has, if I'm not mistaken, it also has this microcontroller, hard microcontroller system in it, but I'm not sure. But I used to work with it also sometime.
Okay, just the problem was how to work on it and what kind of image processing or this kind of problems to solve.
Mm-hmm.
So yeah. It would be very great if you could share us with your tutorials.
Mm-hmm.
And
you will. I will for sure.
Be happy.
Yeah.
So Vivado also could be used for Thoracic.
No, for Thoracic you use how is it called again? it slips my mind, but it is also quite well-known tools for Altera. But it's the same. It's also free, and it's used a lot in Belgium too for different. It depends a little bit. There's no Quartus. That's it. Yeah. So we have Quartus, which is called the Vivado for TerraSync or for Altera boards. But due to the fact that both Altera as Xilinx are using VHDL, you can decide. You can easily transfer every file from VHDL to the Quartus file, Quartus environment, and vice versa. Because that's the main reason for using VHDL. It's independent of the platform that you're using. The translation to the platform is done by Quartus or done by Vivado, but the text files can be transferred easily between the two. Yeah.
Also, there is a question about availability of presentation.
Yes, I will make this available if I get maybe from somebody from TUIT where I should post it, or if there's a Dropbox, I will put the presentation and I'll make it available.
No, we'll make in the website.
Yeah, very good.
Yeah. So, any other questions? So about is Quartus is free of charge or not?
Yeah, Vivado is free and it's from Xilinx, and Quartus is free and that's from Altera. Intel, they have the ambition. I've been talking to the guys from Intel a couple of months ago, and they have the ambition to become very important in this section. And they offer a lot of they have a university program and they offer a lot of things for free for starting with their tools. But same goes for Xilinx. If you apply for the Xilinx university program, you can get this board for free. So as an individual professor, and you say, I want to start working with the Basis 3 board or with another one, I guess the other one is at my desk at the university. But in any case, I got this RT board also for free. So if you ask one board for free every year, they will provide this. The software is for free. The first board is also for free, and this is a good. I think this is for them is a good marketing strategy, because first I got this one for free, and now we ordered 70. Yeah, so that's we know the people from Digiland Europe quite well. So if you would like, I could always get them to contact you if you would like one sample, and then see if you want to buy more or not.
Thank you. Thank you. So is there any other questions, please? So I think there is no questions.
Okay, thank you so much.
Thank you very much for this kind of deep presentation.
Mm-hmm.
And thank you for your time. Thank you very much.
Okay. So good luck with the next presentations and the online schooling, and yeah, and I hope to see you soon somewhere in Uzbekistan or somewhere in Belgium. That would be very nice.
Thank you. Thank you very much.
Okay. Bye.
Bye. Bye, everyone. Thank you.
Thank you. Bye bye.
Thank you for the presentation.
Just for information, the video would be online in a YouTube and in our website.
Okay. Goodbye.
Bye.
Okay.
I'm turning off the conference.
Goodbye. Thank you.
Juda zo'r, ajoyib prezentatsiya bo'ldi.